Uh, on the right, you are seeing the sea surface temperature animation, but I'm going to keep on the some parameter space for the MOM6. I turn off the GM and the thickness diffusion. At this resolution, it's everybody's guess. I decided to turn it off. Initial conditions are from Glorious V-Analysis 1996. I would like to mention that I don't do any sea surface sanity relaxation, which both of them comes later. There is the open boundary conditions Kate implemented to the MOM6. I tested both Laplacian and the biharmonic Smagorinsky with a very high value and with a low value. The reason behind this, the development started almost a year ago, and there was a lot of issues. It was all blowing up a lot, and one of the solutions was I was increasing the viscosity a lot. But I would like to show you some results from that one as well. The vertical mixing scheme, the EPBL, with a background of 10 to the -5. Again, for this place, for the interior Arctic, this is actually a little bit high diffusivity, and I think I'll show you also some results from that as well, some drawbacks. Okay, so this is a daily snapshot. On the left, you see the sea surface vorticity normalized by the Coriolis, and on the right, the sea surface temperature for the Smagorinsky Laplacian with a high viscosity. And this was, again, a year ago, the simulation. So if I go between the biharmonic versus the Laplacian, you can see that the mesoscale features are much more prominent in the case of the biharmonic Smagorinsky with a lower coefficient. The temperature gradients are much more sharper between the Laplacian versus the biharmonic. So we decided to keep the biharmonic after that, basically, because of we like to keep as much as eddies in one way or another, although there is no GM, or we're not 100% sure we are resolving the fully Roxbury disruptive formation. And this is the last 10 years mean sea surface speed. On the left is the Laplacian, and on the right is the biharmonic. You can see that North Atlantic current, the Norwegian current, is much more narrower and sharper. Same for the East Greenland current as well. Also in the Pacific side, even in the Arctic interior, you see the much more sharper and stronger velocities, and we use the lower biharmonic Smagorinsky. So from now on, all the simulations, basically, I will show the results is based on this biharmonic viscosity. This is eddy kinetic energy from the MOM6 Z-star model on the left, and the Copernicus L4 satellite data using the geostrophic velocities on the right. Okay, first of all, this is not a fair game because the satellite data is quarter degree. The model resolution is much more higher. So plus it's using the geostrophic velocities. So it might look like there is not enough eddy kinetic energy in the satellite. But for me, it's much more important that the path and the future of the eddy kinetic energy is similar, and which is in the case of the Norwegian current, that's the case. I can see it all the way to Svalbard, both in the satellite and the model. So we have the recirculation in the Fram Strait. East Greenland current, we have eddy kinetic energy higher as well. What we are missing, which is important, is the Lofoten Basin, which is a quite important place for the Nordic Sea's dynamics. And generally, it's a very big mesoscale activity. I think we are not separating enough eddies into the feeding that gyre location. So this is one of the issues about the MOM6 model right now. But to be honest, even the current data simulation Copernicus HiCom is also suffering from that. So this is the sea surface temperature mean values on the left and the bias from the World Ocean Atlas on the right. I'm going to go again between Z-star and the hybrid simulation, back and forth. The main differences is in the Arctic, they are both a little bit colder, but not too bad. In the Pacific side, Z-star actually is suffering somehow from the boundary conditions or something. It's much colder if you look at the top on the bias. However, hybrid coordinate resolved that issue nicely. Now, but if you look at the Labrador Sea part, the hybrid model is warmer than basically the Z-star model. So there's a gain and loss between two different basins. However, overall, the Arctic interior very similar. Okay, of course, when it comes to the Arctic, the sea ice extent, sorry, and the sea ice area is one of the major to look at it. Blue lines are the NSA-IDS sea ice extent and sea ice area. The models, both the orange and the green ones, is overestimating the sea ice extent or the sea ice area, however you want to look at it. It's almost 10%. It's capturing the interannual variability, but that's not a big success because from the core 2 simulations, we know that basically any force model is showing the interannual variability based on the atmospheric forcing as well. So that's why we are capturing very well the internal variability, but more or less we are 10% more sea ice. There's a little bit, the hybrid coordinate little bit better, but I think within the uncertainty limit, I wouldn't call that it's better in terms of the compared to the Z-star. So this is a similar graph that Hu Kim showed yesterday for the, I think, the global circulation model. On the left, the MOM6 Z-star, and on the right is in the middle figure is the hybrid Eurasia Basin Hofmöller diagram of temperature as a function of year versus depth. And this is the last, right figure is showing the last 10 years of the mean profiles with the World Ocean Atlas climatology. Actually, I'm very, very surprised. Z-star is spot on when it comes to the Atlantic water depth and the maximum temperature. Hybrid is a little bit cooler, but still not bad, which I am not too much worried about this difference. I will show you the reason behind that. The hybrid one is a little bit warmer in the deep ocean, which is, I think, an issue we have to discuss, which has come. Something is interesting, which I've never seen in any model, but both Laplacian and this biharmonic models will showing. There is some kind of evolution in the maximum temperature in the Eurasia Basin. And when I compare this to the Canada Basin, there's a compensation. So heat anomaly is somehow moving first from Eurasia Basin to the Canada Basin and then comes back again to the Eurasia Basin within this 20 years of simulation for this particular case. This is the Eurasia Basin salinity Hofmöller diagram. Actually, it's pretty good if you look, considering that I'm not relaxing the sea surface salinity. If you look at the Canada Basin, the models are showing a little bit different depths, a little bit similar to the Hu Kim's, I guess. The maximum depth is now shallower, and it's a little bit colder than the observations. I think the take-home message in here is actually both hybrid coordinate and Z-star performs very similarly when it comes to the Arctic interior. And this is the sea surface salinity of the Canada Basin. Here we start to see a significant difference from the surface, especially from the World Ocean climatology. And then I'm almost sure this is either with the brine rejection parameterization, which I'm not using, or plus the sea surface salinity relaxation, basically. Okay, so when you do Arctic simulations, generally what you do, you look at the 4 Arctic gateways and the volume transport of this. So here, the circles are the hybrid coordinate, and the star is the Z-star simulation of the volume transport across the 4 gates, bearing from Davis and Barents Sea. All variability is very similar in terms of both models. And if I look at the compared to the observations, except the from, almost all gateways showing a very similar behavior compared to observation within the uncertainty, to be honest. The from, there is a time evolution change, which I need to look at in the more details. I don't know if this is related to the either where I cut the section or the recirculation. I think there is something going on else. The heat transport on the other hand, here is the difference. And other gateways, except the Barents Sea, there is not too much difference to total heat transport. And this is very important because the Atlantic water can only go from or Barents Sea into the Arctic. And here, basically, Z-star is significantly higher than the hybrid coordinate in terms of the Barents Sea. But I didn't look at the impact of it. Probably it should have less sea ice in the Barents Sea compared to the hybrid for Z-star, basically, because there's significant observation evidence that heat transport into the Barents having melting sea ice in that region. I think there was another talk yesterday about the fresh water content. So this is a figure of the every 5 years of MOM6 freshwater content in time, how it's changing. And we can see the increase in the freshwater content. And if you look at the time evolution of the MOM6 Z star, in this case, the freshwater content as a function of time, compared to the either GLORIS or ORS5, we are capturing the similar internal variability. We are a little bit underestimated, and I'm pretty sure this is related to the sea surface center relaxation. Since this is a function of a reference salinity at the surface, and since we are not, again, these are the reanalysis product, they do both relaxation plus data assimilation. However, the MOM6 is completely free run, so I'm happy about that performance, to be honest. So the question was, for me, why hybrid coordinate was performing very similar to the Z star. And I think yesterday the question came, and this is a section, which is the purple section around here, following the Atlantic water into the Arctic. And if you look at it, basically Atlantic water, which is a warm layer here, if in the Nordic seas, it's in the isopycnic domain. However, when it comes to the Arctic interior, it turns to the completely Z, basically. So I think that's the reason that the performance is very similar. And if you look at this was the reason I was telling you that why I don't too much worry about the warm bias compared to world ocean climatology, because my initial conditions are different. It's from the GLORIS data set. So basically I move from blue to orange within that 21 years time period. So I care mostly this difference, why the heat is penetrating down in the hybrid coordinate, which I would like to keep it isopycnial so that it will keep that water masses. Probably some part of it that higher background diffusivity. I think you can do a back of the envelope stuff, but the other part should be probably the Z star and the spurious mixing maybe. To test this, so we try to test some couple of different coordinates just to see if we can make the interior Arctic more isopycnial. In the default case, normally people, probably everybody is using these orange lines, sigma 2 values from the HICOM 1, and the DZs as a function of this FNC if you are carrying over the MOM input file. So that's our hybrid simulation. But I tested two different simulations as well. The first one is the 75 sigma 0 layers rather than sigma 2 layers. And out of the 75, the 50 layers actually is the HICOM's Copernicus Arctic target density. So I just took over their target densities. I interpolate or put some light waters out for that 25. And the DZ is the same as the orange one. And the second simulation, actually, this time I keep the sigma 2 target densities, but I use a different DZ, thickness changes basically. And in this case, we use 2.5 inflation factor every time we are increasing the DZ as a function of 2.5%. The reason behind this version is we are both Blom and the HICOM is using something similar in terms of the thickness changes, basically, just to test how it looks like. Okay, now is a cross section from Norway to Svalbard in the Arctic interior and the Pacific. And the left is the basically HICOM 1 default hybrid case. We have isopycnic layers on the Nordic seas, fully in the Eurasia basin, which is the Arctic interior, and then better Pacific, basically. However, if we look at the 0.25 the inflation factor DZs, actually Arctic bottom becomes isopycnic in this case, and a little bit here, but Atlantic water layers is still Z, geopotential coordinate. If I do the sigma zeros, this time, you can see that the Pacific waters in the Arctic interior is on the isopycnic. This part is fuel isopycnic. What I didn't like about that, deep ocean is geopotential, is this. The Pacific region is, I'm not 100% sure this is good that we have these thick layers in the Pacific case. So I stopped here. The reason behind this, sorry. So it started to become, trying to explain an elephant in the dark. So I think I need a much more objective method a priori, that how can we distribute both layers and Z's. And I think Ian has a talk today, I just saw in the schedule actually, kind of tackling that issue. So that will be very interesting to test his ideas. Okay, that's a typo. Final conclusions are, so we are just finishing developing the semi-decent version of the Panarctic MOM6 model. We both tested the Z-star and the hybrid coordinate. They perform very similar between them. And I'm guessing the reason behind this is basically in the Arctic interior, hybrid turns to geopotential coordinates. So that's it on my side. Thank you.
Thank you, Mehmet. Do we have any questions in the room first? No. Oh, who? Go ahead and unmute yourself.
Yeah, great. I mean, the duration temperature profile looks really great. You know, related to my talk yesterday. So have you looked at the property of inflow from St. Anna Trough?
No, I didn't, but I have enough experience with the NORI-SM. Basically, anytime you have a cold bias, it should be related to St. Anna Trough overflow. So if this looks like good, either it goes under it, I'm guessing, or it's on the surface. Basically, it becomes the isolation layer. So, but I didn't look at in details about the Barents Sea or the St. Anna Trough overflow.
Okay. Another question. So you there's a little bit of warming in the deep ocean, kind of below or lower layer of Atlantic water layer, and you said you don't worry about much. But my question is, you know, at least in coarse resolution simulation, the warm bias in the deep ocean is related to bias in the Jinsea, because the warm bias water can enter the Arctic Ocean through Fram Strait. So if you look at the bias in the deep ocean in the Jinsea?
We checked it, I checked it 250 meter, not below that. And actually it has a slightly cold bias at the 250, other than a warm bias, yeah. I'm trying to remember the seal at the Fram, I think it's 2000 meters. So yes, in theory, I think this can be advective as well. True. I'm trying to remember if I think I make this sections of the Fram, but I don't know if I remember or not, if it was a warm bias in the Fram Strait or not. That I need to check again.
Okay, yeah. Great, thank you.
Yeah.
One question from Bob.
Yeah, thank you, Mehmet. These are really nice results. One question though about your background diffusivity. You use 10 to the minus 5th meters squared per second as the background.
Yes.
Which is actually lower than we've used in the past. Recently, we've tried smaller values, and it actually does seem to help with reducing this kind of diffusive-like tendency. I'm not saying it is diffusive, but the peaks is being smoothed out. Have you looked at have you considered whether a smaller background diffusivity might be appropriate in the microtidal Arctic?
Yes, I have considered that. I didn't run the model because it's very expensive. The reason behind we use it, I use the 10 to minus 5. When the code was blowing a lot, basically I increased everything, including viscosity and diffusivity, so that suppress every noise on the stuff. That's what I started with 10 to minus 5. But yeah, in theory, Arctic has a very low amount internal background mixing. It has even double diffusion, right? It's at cat's tails. So that means the diffusion should be on the order of either 10 to minus 7 or a little bit more than that. So if I have some computer time, I would like to try the 10 to minus 6. Then this is going to be interesting to check, basically. With the 10 to minus 6, if I don't see this penetration, that means this is related to the background diffusivity.
Okay, I'll ask the last question. Mehmet, when you do your experiments, you take the HICOM one, you say out of the box, I assume it's OM4 settings. So there is some thickness maximum as well in that setting,
Yeah.
right? And then when you change to Sigma 0, did you have to change the HICOM 1 code? Because my understanding is like internally, HICOM 1 is always using Sigma 2. So if you provide a value coming from a Sigma 0, it might
You need, I think I asked in Slack, basically you need to change two things if you are changing your target densities in different sigmas. One is the pressure reference and the proper target densities.
Gotcha.
So I changed both of them in terms of that. I didn't play the DZ minimum or DZ maximum. That is staying constant as the previous simulation, which is the HICOM one. I just changed the target densities to a sigma, different sigma, basically.
Okay, thank you. All right, let's take Mehmet one more time. And our next speaker is Dan Amrang here from NCAR, and then we'll talk about regional MOM6 in CSN, progress, new capabilities, and next steps.
Excellent. Thanks, Gustavo. Thanks, everyone, for being here. So this is actually a presentation in two parts. It's about ongoing work that we have here at NCAR and with collaborators. So first, I'm going to give an overview of this project, because it's fairly large in scope. And then in the next talk, Manish will touch on some of the work that he's been leading in terms of the front end that we're working on for developing regional MOM6 in CESM. There we go. So Crocodile, which stands for the CESM Regional Ocean and Carbon Configurator with data assimilation and embedding, is a 5-year project that's sponsored by NSF Cyber Infrastructure for Sustained Scientific Innovation, CSSI. I guess I'm saying this for a couple of reasons. One of them is that it's a 5-year project. We're 18 months into it, so we still have a fair amount of runway in terms of what we would like to do. And also to emphasize that this is, coming from a division of NSF where the deliverables are software. This is coming from the SISE directorate. And so while we expect to do science and get some capabilities, we're really emphasizing the Git repos, and they care about how many stars you have on your Git repo, these kinds of things. So it's an opportunity for us to really focus on building a community around software we want people to use. Okay, so what are our goals? We want to make setting up regional ocean modeling within an Earth system model a lot faster and easier. The premise here is that there's a lot of overhead that can be taken care of automatically, and Manish will showcase some of that. We want to make data assimilation, give it a home in how we develop regional models. And this is the case at a lot of other centers. We're not there yet for Earth system modeling, right? And so this is an opportunity for us to really integrate observations into this workflow. And the final and maybe the hardest part is we want to build this and then sustain it, right? And have people use it, get in the door, and then keep them here. So those are our goals. And so after 18 months, I'm happy to report that it's not just us at NCAR who are working on this. So we started off with a collaboration with folks at WHOI, and I'll talk more about that. They're really interested in the carbon cycle perspective of regional modeling, and particularly for marine carbon dioxide removal. Yesterday, folks were mentioning efforts on MOM6 as part of COSIMA and at Australian National University. We've really gotten a jump start, especially from the work of Ashley Barnes, who's a grad student. He'll be graduating soon. Ashley visited us last summer for 6 weeks, and we were able to fork his package, and it's been really fabulous. And then we've also had a host of students and interns visiting so far. So we're looking forward to growing that collaboration. Okay, so why should you use an Earth system model if you're interested in regional oceanography, right? Maybe you're interested in modeling some bight, you want to force it with some atmospheric forcings. Why should you hitch your trailer to something that can also simulate land ice over millennia, right? So I think there's a couple of perspectives on this problem, or this question. One of them is that when you use an Earth system model, you get a lot of infrastructure that's really powerful for regional modeling workflows. So things like case management, in interpolating fields to different domains, the ability to run long simulations in a really streamlined way if you're interested in climate timescales, the ability to add on coupling to across different parts of the Earth system. Another piece is you get the open rapid development that we have associated with MOM6, right? And this isn't the case for all regional models. This is a nexus for developing ocean physics. And then, as Mehmet really just nicely highlighted, there are options within MOM6 for changing up your vertical grids. You can have a low resolution regional model because we have mesoscale and submesoscale parameterizations, right? That's not the case for other regional models. So if you're interested in, especially like these Earth system climate applications, you get a lot from using these Earth system modeling tools. Okay, so that's kind of the pitch for why you might want to use it from the regional side. And then why are we, the G in CGD does stand for global. Why are we interested in regional modeling? Well, it's people, I think that folks are well aware that we can simulate climate, but we do it in coarse resolution models. And that's likely to be the state of the art for the foreseeable future. And the impacts at regional community scales are not resolved. So this gives us an opportunity to dynamically downscale. Another thing I'll point out is that regional models can be fit for purpose. And so sometimes we joke that global models have no purpose, which is not to say that they're not useful, but they're not designed with anything in mind often, right? We look at these large scale metrics, but I loved Fred's talk yesterday where he said, well, look, we found this, the cooling in the Southern Ocean, but that's an emergent property, right? It's a discovery, and then you can go and poke around. Whereas, for a regional model, you can say, I'm interested in this process, and we can build a model for that kind of thing, right? And so, in a sense, if you're interested in a particular problem, there are benefits from having a focus in your development. Another thing I'll point out is, there's a fascination, preoccupation with moving climate and Earth system modeling to very high resolution, kilometer scales. But of course, we are limited by computational power, right? We can shoot up the resolution, we can have more components, we can think about ensembles and longer durations. We feel like these regional models, if you're interested in very high wave number air-sea interactions, for instance, this is a way to kind of short circuit and get to these very high resolutions. Okay, so I'm probably preaching to the choir. This is partly reflecting my own journey from someone who does only global modeling to now thinking about regional models. But regional modeling is important, right? And we want to support it at NCAR, right? We want to grow a community around this. The problem with that is that it's a challenge to how we provide community model support, right? A success might look like a proliferation of folks working on different model domains, but we can't provide scientific support across all of these different domains. So part of the question here is how do we transition, how do we provide tools so that people can take this next step? So the goal of this project is to accelerate regional ocean model generation and provide tools so that folks can tune it for purpose. And so for a while now, I've had this kind of pretend pie in the sky Jupyter notebook. I'm really excited that now Manish is going to show off it actually exists. You can't read this because this is an extremely small screen, but the vision is you open up a Jupyter notebook and you have some Python-based tools to set up MOM6 in Marble, to configure your data assimilation, some options to save the configuration for reproducibility, and then to plot some diagnostics and start looking at output. So the philosophy is that we are not going to scientifically support these models, but we can provide the chassis and the car and the tools so that you can tune this up for your own purposes. Okay, so for the rest of the talk, I'll touch on some of the major activities that we have ongoing as part of this project. So first of all, we would like to build these tools. We also want to ensure that there exists a pathway towards scientific success. So thinking about how can we reproduce existing setups. I'll touch on some of the work by our WHOI collaborators that's focused on ingesting lots of data about the carbon cycle, talk about the update advances in data assimilation, and then the last part is this Jupyter front end, and I will hand that off to Manish at the end of the talk. Okay, so a first step is this question of, we built this thing, can we, when we run MOM6 and regional MOM6 and CESM, can we recover results that people have found before? And I think the driving force behind this has been Gustavo, with a lot of help from Fred. So one thing I didn't know when I got here is there's actually like a great depth of expertise in regional modeling within the ocean section. So that's been really cool. And so our approach here so far has been to say, okay, there are examples of MOM6 published cases that have been worked on by a broad community. So one example is the NWA12 configuration, which is led by Andrew Ross, Charlie Stock, other folks at GFDL. Another is the Carib 12 configuration. This is a new publication by Giovanni Sejo, who was a postdoc here and recently started as faculty at the University of Puerto Rico. So we have a couple of hypotheses here. The first, kind of the order one, is can we take a MOM6 configuration from NWA12, plug it into CESM, and recover scientifically similar results? And so the workflow there has been to, at first try to reproduce as closely as possible, get the same kinds of physics and stuff, and then slowly to kind of add in our own, physics changes and think about boundary conditions, these kinds of things. And Manish will touch a little bit more on where that work is going in his presentation. And then there's a second step, right? Because ideally we would like people, we would like to have a lot of the tools that you need to get to the point of an NWA12. We would like to have those in a streamlined workflow, right? So when someone sits down with their Jupyter notebook, what knobs do they need to have in order to get to this point? And so that's work that Aidan Janney is working on with Giovanni and Manish and other collaborators, basically saying, okay, if we just use this Jupyter notebook, how close can we get to, for instance, this Caribbean setup? So, we're trying to be a little bit hands-off and say, well, we're mostly going to give you the ability to run the model, right? And what does that mean? That means the grid, that means the forcing files. But we also want to have a gallery of cases that show you, look, you can get to the point of having a scientifically useful model. Okay, next I'll talk a little bit about the carbon cycle side of things. This is actually the origin of this proposal, was we were interested in how to support marine carbon dioxide removal research within this community. And I think that the challenges around MCDR exemplify a lot of why you might want to have a regional purpose-built model, right? You're entraining a lot of parts of not just the physics, but the ocean biogeochemistry, ecosystem effects. You're really interested in point source, very small releases, for instance, of chemicals into the ocean. What's their subsequent evolution? How is that affected by small-scale processes? So in short, to say, something very hard to do in a global model. And so folks at Woods Hole are pioneering thinking about this in the North Atlantic. And one of their goals over the next decade is the development of what they're calling the Ocean Vital Signs Network. Basically, if you think the Northwest Atlantic wasn't instrumented enough, they're going to do even more of it, but with a focus this time on carbon cycle processes. And I think one of the driving motivations here is that there's people who are going to be dumping stuff into the ocean, right? And we don't even have a good understanding of the baseline parameters of a lot of the carbon cycle. And so a lot of this focuses on the development of novel observations and then needing a way to confront them with a model that can reproduce a lot of the salient processes. And so the drivers behind this are Susan Weifels and Rune Nicholson, who are on this project. We've also brought on Enrico Milanese, who's a full-time software engineer working with this. So when I say, we're interested in confronting models with observations, that feels a little bit like a data assimilative piece, and that is indeed where we are hoping to go. And so what Enrico has been working on for the most part, is developing data sets that we can use for near real-time data assimilation within regional models. And so this is a collaboration between Enrico and Helen Kershaw, who's in the data assimilation section here at NCAR. And so they're using this slick new Parquet format, which is a way of storing data that's really meant for rapid access of very large data sets. And so they're at the point now that they have spray gliders, LODAP, Argo temperatures, which I'm showing here. But this is also a template so that when they go out and have some newfangled observation, we can also be able to ingest that into our data assimilation workflow. It's called Croco Lake. I think that's attributable to Manish. So thank you, Manish. Okay, and then there is a data assimilation side of this as well, right? And again, thinking about this, for purposes of making your model better fit a particular observational data set, but also, in the weather world, data assimilation is a key part of how a model is developed, right? You are constantly confronting a model with observations. You see where the model is going wrong. We want to move in that direction, right? With Earth system modeling, and this is a chance to do it in the regional ocean. I feel contractually obligated as a DA person to briefly contextualize what we mean by this. How do we do, and so we're talking specifically about ensemble DA. How do we do ensemble DA in a regional ocean framework? This is global, I'm sorry. So what you do is we have to run a large ensemble of simulations simultaneously, right? And so right away, your computational cost goes up by a factor of at least 40. And so the spread of the ensemble represents the uncertainty in what your ocean state might be. You can advance your model for a time step. When you encounter observations, you reach into the model and use an observational operator. And that basically says, okay, I have this model state. What's the thing I can compute that's analogous to my observation, right? So that's how I can compare apples to apples. And it is that comparison between model apples and data apples, the misfit there, that's the gold in data assimilation, right? And so by taking that misfit, we can then nudge increment each of our ensemble members to something that is a better fit to the observations in a way that reflects, the uncertainty in the model and the observations, a kind of tug of war there. And then you can continue advancing your model. So that's kind of the philosophy behind Ensemble DA is we run lots and lots of versions of the model, and then we're kind of moving them as we go along. This is useful for a couple of things, right? This is great for initialized prediction. So if you want to make a prediction of your state, you want to have a good model, but you also want to have a good starting point. But it's also useful for looking at parameter estimation and model bias. So this spread can come from model state uncertainty, but it also can come from a spread of your parameter values. And that's something that we have explored doing data assimilation in the Marble, in our carbon or BGC model, as an example. Okay, so what are we doing on this front? Our work now is in part, I don't want to say transitioning a lot of really powerful Fortran-based data assimilation infrastructure into Python environments. And so Helen is leading this effort on PyDart Diags. So this is Python front ends for these Fortran-based DA codes where you previously had to edit a lot of name lists and do things in shell scripts. We're now at the point where we can do a lot of these basic functionalities of the data assimilation in the Python framework. And I would say too, we have Dart for nearly, with the exception of the land ice, which may never happen, every component model within CESM. So we hope that these advances can translate across the Earth system model. I wanted to highlight one recent milestone, kind of granular, but we can now, a cool thing is that because of work that Altair did, we are able to run these ensembles through this multi-instance capability as part of our Python packages. So that was exciting. Okay, so Manish's talk is up next. I wanted to conclude. So this is a place where I would ask for input from you all, this community. This question, right? So in order for us to succeed, we have to get people hooked into this thing, right? I mean, I literally have to write these annual reports and show how people are using the software. And so we are being a little bit aggressive in terms of trying to bring people in early and often, and also unabashed in trying to get them to contribute code. Okay, so how is this working? So we're going to host this initial community workshop October 13th to 17th, and it's going to be here. And Gustavo mentioned this yesterday as well. So there's going to be a Mom6 tutorial piece of it. And then we're going to have this is a proposed agenda, so feedback welcome. We're going to introduce this Python framework we have. We're going to we're going to have a workshop on Git and collaborative workflows. I promise I'm not going to ask anyone to star the repos, but and then envisioning a kind of hackathon, right? Can we, are there small projects we can do to incorporate new vertical coordinates or have a domain? So we have travel funds each year for the next 4 years to bring 20 early career students here to work on this. So it's a really cool opportunity. And for those of you who have experience in building community software, I'd love to get your inputs on how to make this successful. Also, if you're interested in receiving future announcements, please email me and let me know. Okay, so yeah, that's what's next. So we're going to host this initial community workshop. We're working on a gallery of use cases and notebooks. Something I didn't talk about today, but that Mike Levy and Keith and others are hard at work on is advancing regional BGC capabilities with Marble. We are going to hire a SciParks intern this summer to focus on this kind of reproducibility aspect. How can you export a configuration so that other people can reproduce your configuration? And yeah, our repos are public at GitHub, Crocodile CESM, and so I'd really welcome any questions and feedback. Thanks a lot.
Thank you, Dan. We have time for a few questions, starting from the room first. Bob, yeah.
Can I?
Let Bill go.
Oh,
You go.
yeah. Just if you get somebody hooked, and it's pretty loose on the hook, but you got them hooked. How many, say through the tutorial or something, do you have any resources to sort of handhold to a workable thing to really get them hooked? Or is that really, I mean, it's always been a big problem how much you can afford to do that. Do you have any capability of hand-holding, basically?
We have, so we're trying, the vision is that we have a line a little bit, right? We want to handhold to the point where someone can run the model, can look at output, and maybe see that it's wrong, right?
Yeah.
We do not want to be in the business of addressing a lot of specific problems across different regions. So I guess that's our hypothesis, is that that's enough of a hook. And that, and not to say that they're going to be left alone, right? But I guess that's where the community,
Yeah.
But that's what we feel like we can do. I mean, what do you think? Is that enough?
Well, yeah, you got a plan. I think that's the important thing. At least you've got some lines, and people will understand it. And from your last statement, you think some community handholding will release the burden to have a formal procedure if you keep people in contact with each other, and we can do it that way. But
That's the hope.
it's a long. I mean, it typically is a fair jump from a tutorial where you learn some things but not everything to actually getting a functional thing going. You can do science. That's what I'm asking. So
Yeah.
Bob, then Baylor, we have like 2 minutes.
Okay, we have 2 minutes?
Yeah.
Okay, so in those 2 minutes, maybe this is for discussion later.
1 minute.
What are your wish lists for additional capabilities going forward that you don't have the resources for? So two-way nesting would be awesome, but we need to scope out exactly what properties we want that to have. Regional PIDEs, there are a whole wetting and drying. There are a whole list of things that are kind of coming online.
Yeah.
Do you have your wish list of what you think would be the most impactful things for the regional configurations that we should try to prioritize?
Yeah, that's a great conversation to have. I mean, one of them is CICE ability, to run CICE in parallel. We have some TIDES capabilities right now. Yeah, I will return to you with a longer list. Yeah.
Mine is very quick. When you have this tutorial, which I think is a great idea, it would be great to mention to the students that they should definitely go to E3SM meetings and EVE meetings and Destiny meetings and present their results, showing them that this system works well, gets you kilometer scale today, not in some ill-defined future, and actually has a fully coupled system. I think that would drive a lot of interest and also maybe quiet some of the claims that are being made by some of those other communities.
Yeah, I would like to see that with the caveat that, okay, so this is also at the top of our list. It's not coupled right now. I mean, we don't have, it's data atmosphere. We would love to do coupled. So.
But even so, I mean, I think this will in the very near term have very powerful capabilities that would be good to kind of get into those conversations with other groups that are approaching this from a global scale only.
Yeah. Thank you.
All right, let's think Dan one more time. And our next speaker is Manish Venumudula. Did I say right?
That's perfect.
And Manish is the new software engineer in the ocean section. I think this is your first Ocean Model Working Group meeting.
Yeah,
Welcome.
use this computer.
Yes, you can.
You can also, yeah.
Do you see his software?
Yeah,
Is it the same one?
yeah, that's such a.
Okay, you talk about regional MOM6 in CSM, new setup software, user experience, and open development.
All right. Thanks everyone for being here and listening to Dan and I's talks. In this talk, we thought we'd zoom in on one aspect of the Crocodile project, specifically the part where like the users are actually setting up the regional model, i.e. like kind of a lot of the software Python stuff that we're working on. And so just before we get started, because I'm pretty new to this, I'd introduce myself really quick. I'm a new software engineer here at NCAR. As of about 7 or 8 months ago, I got my bachelor's in climate and computer science out of Michigan, and I like playing the saxophone. So that's me and what I do here as I was hired under this project. So just to zoom out a little bit, Dan talked about 4 different aspects of Crocodash, this Northwest Atlantic regional domain that we're working on, this data assimilation piece, and this observed data lake that we have. But most importantly, in my extremely biased opinion, is this dashboard, this user dashboard that we're working on. So I thought in this talk, we go over like 3 different things. One, I would discuss the structure of what we have so far and let's go through a little demo of what you can actually do at this state. Like literally you can download it today. And then talk about some of the issues we're working on. And I'd really appreciate input if any of you have solved these issues already. And then finally, and most importantly, is talk about our next steps. And Dan has talked about this too, but it is what tools can we implement to help you? So we have our workflow right now, but we want to both garner interest in the project by like making tools that you could use and try to think about where can we go next with this project. So please keep that in mind as we go through the demo and you see anything that's wrong that you want fixed or you have new things that you'd like to see. So with that, I'll just kind of talk a little bit about the structure of what we're doing. So first part, the idea is that we're having a Jupyter notebook that we're doing Crocodash through. And this is just really quick. It's a pretty easy logic behind that. One, it's a nice user interface that most scientists are familiar with. Balance alongside that, it's really close to the code. So if you want to write your own modules or add your own forcing data sets, it's pretty easy to plug in because after all we're doing is writing a Python package. So yeah, I don't really know what's going on behind it. The next thing I'll talk about is a Crocodash structure. So Crocodash is a Python package that really specializes in bringing a bunch of MOM6 and CSM tools together. That's what it is on top. It takes all these cool tools we have lying around and brings them into one workflow. And we kind of subscribe to this 3-step process of setting up a regional model. On the top left, we have grid generation, and then we have CSM setup. So now that we have our grids, can we tell CSM what our grids are, what actually region we're going over? And then finally, in our bottom right, generate all of our forcing data. So that's going to be, as well as, boundary conditions, initial conditions, and stuff like that. This ties pretty directly into some MOM6 tools that you may or may not have used. For example, for grid generation, use MOM6 Bathy, which is made by Alper, as well as for CSM interfacing, Visual K-Shen, which I put in a picture of Alper here, just so that you know it was him. But this is an amazing tool that helps us interact with Scene, which is kind of like CSM's like case management software that is a really strong way of interacting with CSM in a way that doesn't fail as easily as, using subprocess or some other random tool in Python. Okay. And then finally, and this is a really cool thing, is we also use Regional Mom 6, which is a Mom 6 tool for setting up all of your input data, boundary conditions, initial conditions, stuff like that. And that was made by Ashley Barnes from ANU, who's a PhD student there. He's a wicked coder and an extremely intelligent guy who helped us out in the beginning with setting up Crocadash when he visited. And Dan mentioned that briefly. So that's kind of the framework we're working on. We got a Jupyter notebook. We tied together a bunch of tools from different aspects. And we try to make one workflow that we can all go through. So the next section, hopefully it works. Okay, we have a video demo of what we're doing because everyone knows demos work perfectly when you show them to people. I'm gonna try to play it here. Okay, let's see. There it is. Okay. And this is a pretty short demo. It's about 3.5 minutes. And I'll go through those 3 sections of grid generation, CSM interaction, and input data setup. So that's all your like ocean boundary conditions and stuff like that. You'll notice this is in Jupyter Notebook. And on the right, we'll just kind of highlight what section we're in. And I'll be pausing throughout this, so don't get like jump scared or anything like that. Oh, okay. I kind of jump scared myself. This first step that we go through, so I'm just going to start going through this. So the first step that we go through is we have to actually determine what region we're going over in our, what we're modeling. And how we do that is by defining a corner point in latitude and longitude and determining how long are the lengths of our regional box, like what our region is. And so in this specific function, we have an X star and a Y star, which is longitude and latitude coordinate for one point, as well as how long our longitude is 4 degrees and our latitude is 3 degrees. I don't know if you guys can see this super well, but that is a region that we're using. We can also determine a horizontal resolution and stuff like that. And because we want to showcase a cool tool inside of Crocadash for choosing the Panama domain, so that's how we can determine our region. So if you were to just get started with regional modeling, this is probably one of the only steps you have to touch in our workflow, at least in the beginning. So you run it, you're like, okay, there's my domain. The next thing you got to do is tell the model or Crocadash, what does our ocean actually look like, which means topography. So we pass in what the grid we just generated into our topography objects inside of Python. And this is where we introduce our first data set. So one of the things that goes on with any kind of modeling is you start with, your forcing data sets, your bathymetry data sets and stuff like that. So we're using through Crocadash GEPCO, which is general bathymetric chart of the ocean. And this is a really easily downloadable data set that's 4 to 7 gigabytes, so you shouldn't have any problems with it. But basically what we do is we take that data and we regrid it onto our own grid that we've just determined. And I want to say this all in real time. I haven't sped any of this up. We're using XCMF in the background to do all of this. And because it's a small domain, it doesn't take very long, so it finishes in a few seconds. What you see printed out here is just in case it fails as you use larger and larger domains. For example, on the Northwest Atlantic domain, you might need more resources. You've got to be careful with what you do. So just to show you that we actually did get Panama, we're just going to plot it really quick. And so if you're familiar with the area, the north is the Atlantic, the south is the Pacific. And this kind of lets me segue into this cool tool that we have here, is that with Crocadash, with this tool called the Topo Editor, which lets you edit the bathymetry that you're working on. And in some cases, when you're doing regional ocean modeling, you're only worried about one basin or another. Especially in the Northwest Atlantic domain, for example, it covers a huge section, right? And we don't actually care about the Pacific in that section. So we just kind of want to erase that and save us some processing time. So here in this next little part, we're actually going to erase the Atlantic because we only care about the Pacific. That's arbitrary. So I'm going to really quickly go down there and load the tool. And this is called the Topo Editor. It comes out of Mom6 Bathy. It's an example of a tool we're like kind of combining into this workflow. Of course, it's still a work in progress, and you can look at different visualizations like a land mask or a basin mask of what basins you have in the Panama domain. I'm going to erase the Atlantic here by selecting the point in the Pacific and erasing it. And so, of course, I'm just like moving my mouse around or whatever. And if I look up, that's it. We've erased out the Atlantic. We have just the Pacific. And this is a pretty specific example, but it's just one example of the tools we can set up inside of a regional model to make it easy. So you don't have to like worry about the random things that go on that you want to do while you're regional modeling. So that's one example. I'm going to scroll through some views just to show you that it worked. But then finally, the last thing you do in grid generation after you define your domain and your topography is you need your vertical grid, which is just how many layers of the ocean you have. And we're using some pretty standard defaults here. And there's a lot of avenues of development that we can go into there. But you can notice that there's more layers at the surface because you want to resolve smaller vertical layers there. something like that. My boss told me to say that. But that's the grid generation part. So that kind of lets us tell our model what are we actually modeling. Now we can actually interact with the CSM. Tell them, here's our grids, set up our case. And so in the first part is where we actually put in our CSM sandbox. So that's pretty much the only part where you're really talking about the CSM, as well as our input directory, our case directory, and a case name. It's called V2 because I ran this already, just to be careful, even though it's a video. And so I'm just determining some paths. And this is where we actually interact with the CSM. It's a beefy step where we pass in our grid, our vertical grid, our topography, all the stuff we just generated, as well as all of our directories, so that now we can set up all the information we need for a regional case. And this takes a little bit of time, but it tells you, all right, we created a case successfully that's ready to be, used at the regional model. I'm actually going to go there in my terminal window. Ignore that spelling mistake. And we can look at it. And if you're familiar with the CSM, this should look like what you expect for a CSM case. I'm actually going to print out the parameters that we put in to tell mom, like, we're in a regional domain. And if I pause here really quick, you'll notice that we have our input directory, our grid file, and topography file, which is basically, we put all the parameters to say, this is a regional model, CSM. Now you know what to do, which is great news. So that's it for CSM setup. We have got the grids, we've got the CSM case setup. All we need to do is generate all of like our OBCs and stuff like that. So how we do that is a two-step process. We basically pass in all the information we need, and then we regrid it onto our domain. And so most importantly, the thing I'll highlight here is this is where we introduce time dependence. So we got to determine where our initial condition is, our boundary conditions and stuff like that. And we use glories in the back end. And so what this function will do is it'll let you put in all the things you want. Right now, I've put in 2020 for our date range, as well as some title information. It'll tell you exactly the steps you need to access the data. And accessing data is one of the hardest parts of the regional modeling framework, because it just takes time. You're plugging in a lot of different pieces, and it's something we're actively working on. This doesn't take very long. It's just tells you what to do on how to get the data set that we're currently using, which is glories. There's a lot of to-dos on here because this is a workflow in progress, but it is something you can work on, you can do right now. I've already gotten the data, so I just copied it in really quick. I'm going to process it. This is the beefy step. I've sped it up 50 times because it's regridding and it takes a little bit of time. I would say it takes about 15 to 20 minutes. And at the end of that process, what you get is a ready to be built regional MOM6 ocean model inside the CSM. So all I need to do here is go to my case directory. I'm already there, but why not go there again? And I just need to build and submit the case. So I'm really going to quickly do that. If you're familiar with how derecho works here at NCAR, you use UCMD and all that. And that's actually it for the regional model case. It probably take about 15 to 20 minutes to set up. And for a new user, it would probably take, an hour or two. And we're not promising scientifically valid regional ocean model cases. We're promising an easy way to set it up. And it cuts out a lot of complexity. Like, say, for example, you switch the X and Y dimensions in one of your forcing files. This helps you figure out what that process looks like. So you can start doing the science that you actually want to do. And just to show you some results, and I made no changes after this. I just submitted it, ran it, and I don't know if this looks good or not. I'm not really a scientist, but here's that to me. All right, so that's kind of it for the demo side. I hope you stuck with me throughout this. But in case you weren't listening, I had something for you. And this is one sentence you take back if you weren't listening, is that Crocadash, as it currently stands, is a quick and efficient way to set up regional ocean models at the CSM in 3 steps: grid generation, CSM setup, and all of your input data, so your forcing files and stuff like that. That's what Crocadash does currently. So I'll point out really quick that this is all open. Dan mentioned this, but we have a GitHub organization site where you can, get all your repos and the Crocadash stuff. And as of tonight, you can actually just clone the Crocadash repo and get started. It shouldn't take very much longer than that, especially if you have derecho, which would be really quick. So definitely check it out. We're always there. We're always looking at issues. So me or Alpha will comment on there immediately, because that's a lie. We won't comment immediately, but we'll be. So that's that. In this next section, I wanted to talk about some of the problems we're having, and our next steps, which is where we'd appreciate a lot of input on anything you know about this, because I'm sure we've missed a lot. Just try. So what we're working on as part of this is not just tying all these workflows together. It's just trying to improve how we make boundary conditions and stuff like that. Obviously not developing new stuff, but how we generate them. And so we've been working on the Northwest Atlantic, and what I'm highlighting here is 2 different pictures of the northern boundary. On the left side, you notice that there's actually there's no data over this land section, and there's data on the right side. And basically what was happening is when we ran with part of the northern boundary missing, we were actually running into, it was crashing after about 10 minutes with pretty insane surface height errors and stuff like that going on. And we didn't quite know why that was happening. And so really quickly just filled it all with zeros and saw if it worked, and it was fine. And on further discovery, it seemed like if we put a real value in the northeast corner, as well as a few points along the coast, it wouldn't crash. And when we changed the values, it didn't make much of a difference in the answer, but it was very interesting. And I'm sure we're missing something. That's one of the problems we're currently figuring out is, why do NANs and OBCs over land result in crashes in the model? In some cases, not all cases, just in this specific case and that we've been working on. So that's one thing we've been thinking about. Another thing that we're working on is, this is a really cool fish picture, but Marble is a BGC model that we run with MOM. And one thing we're working on is creating Marble OBCs for MOM. And this is something we're currently in development, but what we've noticed when we put it into MOM input, like, you know, we're using abiotic tracers, we'll put in scalar values for, or you can files, which is how MOM input works. Noticing if we change the scalar value from like 2000 for an abiotic tracer to 2100, it actually made a change in the temperature and salt boundaries, which is probably because we're like leaking memory or doing something crazy. But if anyone has come across similar problems in registering tracer segments or something like that, it's something we're working on. So our question here that we're working on is, why do changes in scalar values of OBCs for abiotic tracers and Marble impact our temperature and salinity, which is just something we're working on. And then finally, one other thing we're working on, and I didn't personally work on this, by the way, this is all work Crocodile is doing, I'm just like mentioning it here as nice things we're working on, is the Northwest, this is again a Northwest Atlantic example, is that along the eastern boundary, which is this left figure here, you'll notice that our meridional velocity is going crazy. And one thing that, so this is work that Gustavo has done, I'm just mentioning here. I'm not a scientist, so I'm not going to talk too much about it, but our GLORIES reanalysis data set that we use for the boundary conditions is forced from ERA 5. But the default atmospheric forcing that we're using is JRA. And we think because of that conflict, we're getting issues at the boundaries. And so if we look on the right, this is a curtain plot of the edge of the MOM6 domain, as well as the east boundary. You notice that the temperature changes a lot more in our MOM6 domain versus the boundary condition. And that kind of brings up our next question is, what is the best procedure for NWA for selecting combinations of OBCs like GLORIES and atmospheric forcings like JRA? And can we generalize that across all the regions we're using that we set up through the Crocdash workflow? So yeah, so those are like 3 different things we've kind of been working on. Of course, there's like, 200 different things that are going on below surface, but those are 3 kind of cool things that we can talk about. And that kind of segues into our next steps feature. So what are we thinking about in the future? And this is where we'd like input on us. Actually, don't do all that, try something else instead. One thing is dynamic downscaling with the CSM. So Dan mentioned this earlier, but we have CSM global stuff that we'd like to use in the regional setting. And this is a pretty natural extension of what we're currently working on. We haven't started, but it's an idea. Secondly, is easy input data setup. So one of the things that kind of breaks the immersion that Crocdash has is you need to generate lots of different data sets, like your bathymetry data set, GLORIES, CSM, tidal data, all that stuff. And that takes time and effort. And however good your APIs are from one data set to another, you're going to run into issues just based on how big it is. And so one thing we're working on is, how do we make that an easy process? That's not, and then there are great ways to do that already. So it's just something we have to figure out ourselves. This is an interesting aside if you're using Derecho, is we've gotten the GLORIES data set on the RDA for our regional stuff, but it's daily files from 1993. So if you have any use of the data set, definitely check it out. It's an easy way, so you don't have to use the API or anything like that. So yeah, that kind of concludes our next steps and our problems. And I just want to leave you with 2 sentences about Crocdash, and I'm going to read these verbatim, which is horrible. And then I'm going to talk about our question that we have for all of you. And it's that Crocdash is our front end for tools to accelerate regional ocean modeling with CSM. That's kind of like basis of what we have. And then 2, it's a collaborative software. And most recently, we've put in like regional MOM6 and Visualcation and all these tools into Crocdash. So if you have other tools that you want to be as part of this software, come talk to us, because that is something we would absolutely love to do. And then finally, what tools, again, I'm just going to repeat this question. What tools can we implement to help you? Is there anything that you have problems with or you want implemented in the future? And I won't leave us with that question because it's really weird when there's silence afterward. So I just want to thank everyone for listening. And if you have any feedback on anything we do in this workflow, we would love to take it. This is still a thing in development, so we're in a good place. As Dan said, we have a lot of runway in this project to work on it. So thanks for listening.
Thank you, Manish. Questions from the room first? Justin?
Just a quick question, Manish. Kind of a data and access question. You've probably been testing this on the ratio.
Yep.
If you're on another computer system somewhere, can you envisage any challenges if you're working on another computer system? Have you thought about that?
Yeah, so I guess 2 points. Crocodiles can be run on your personal laptop. If you don't have CSM ported, it's not going to run. But if you have CSM ported on your machine, theoretically, and we haven't done like really any testing with this, but it should work. That's the goal. So it's independent. It's theoretically independent of derecho. So we're still using like, for our data, it's all open and accessible. So you can just get it online. And there are steps that are listed in our demos to do that. That's the idea. Derecho speeds up the process considerably because we've already gotten the data here. But yeah, that's the.
You have a question online from Yao. Please go ahead.
I would like to know if when you are trying to use Crocus Dash, do you have to have the MOM6 and the CSM already downloaded or cloned into your laptop, or by just using the Crocus Dash, you can access those codes as well?
So how it's supposed to work is you have CSM and MOM6 already on your computer, and then you can use Crocodiles with that framework, because what it does is it actually looks for your CSM to like connect to and create your cases. But you can run it on your personal laptop just to get maybe like the forcing files or like your boundary conditions or stuff like that, and then move them into your MOM6 or CSM. So like when your computer is down, you can still use Crocodiles. If you just have to like clone CSM on your own computer, and it won't run, but it will still plug into all the things that you need to. Does that answer your question?
Yes, thank you.
We go to Bob, then Moment.
So one of the things about MOM6, we have pretty vigorous addition and then obsoleting of parameters. Things come in as they're added, and then as we figure out better things, they get obsoleted. Is there any way that that could be somehow tied into Crocodash so that either we could identify when people are actually using capabilities that they want to keep before we obsolete them, or to provide encouragement to move to newer and better things as we fix things like the bug in the northwest corner where the NAND causes everything to go bad. We're going to fix it, but we're going to have to leave a runtime parameter to recreate whatever it's doing if it has answers. How do we tie that into this kind of creative destruction mode of quality control in MOM6 for Crocodash users?
Yeah, so that would be like kind of like you would put out like new versions of the code that like put in warnings and stuff like that on like things like this. Yeah, same thing as MOM6. And then we could also think about like how it could be like get feedback from users on what they're using specifically, like I don't know, get like metrics and stuff like that. And the idea is Crocodash. So like having something like that so we know what people are using. Is that what you're kind of getting at? That would help.
I wonder too, like we're talking about these angles for reproducible code, and then you would like to have a small file or something, YAML, that has the parameters, right? And so maybe there's a way we can have a cookie like creeping on what people are doing, or encourage people to share these files.
Yeah, we actually generate that with the MOM parameter doc files and things. So, but we know what people in the consortium are doing because we ask them. There are hundreds of forks of MOM6. We have no idea what people are doing when they fork it because they don't have to tell us. And people can download the code without even forking it on GitHub. So that one of the challenges we have, we're guessing at what people are using when we're saying, okay, we have a new parameter date, we have a bug fix, we can obsolete that. It's one of the points of weakness of the system that we don't actually know what people are doing.
You have a little box and you say anonymously report usage statistics for the development,
Well,
yeah,
maybe through Crocodash or something.
Crocodash would be a great feature for that.
Yeah. Alfred, did you have something to add there?
Just a comment of one way we can address this compatibility issues, semantic version, and where we, tie Crocadash version with the CSM MR6 version we're running. So if they are incompatible, then the user would know and switch versions. Yeah.
Cool. Moment.
Yeah, very nice talk. And my question is in similar direction, but it touches more on the forcing data set side. You said there will be problems because there's so many different forcing sets, and you showed one. And if you want to make it, and that will be always there because you can't control what forcing sets that people use, right? So, and that will cause issues.
Yeah.
Do you think about having something like curated data sets, like saying, because there's Crocadash and then there's a standard set of Bathymetry, but also like data atmosphere and so on, so that they can start from that? Or how do you like reconcile that?
Yeah. So right now we actually just tell people what data sets to use. So one of the things we're currently working on, we just started implementing, was this kind of data access module, which lists functions and data sets that we actually can use with the workflow. So having something like that tells people what is Crocadash actually able to use, and the rest use at your own risk. Is that kind of what you're getting at? And so write some good docs is what we're working on with that.
I mean, I think too, I think there's a sense that if we prescribe that people have to use an ocean reanalysis that was forced with the same atmospheric reanalysis, that's a constricting, it's a constriction on what people can do. And so I guess one of the questions we have that Manish also posed is there a robust formulation of how you might be able to mix and match these things and try to kind of patch over some of the inconsistencies among them? That's, I mean, maybe as much a science question as a development question.
Yeah, I agree, but yeah.
Then I just question, how much freedom should you leave to the user to define that? Because you expect that someone that's actually run this kind of things should have an idea of what they're doing, or at least have the freedom to experiment with different things.
Yeah, I mean, I feel like that falls a little bit into this philosophy where we will give people the power to shoot themselves in the foot. And yeah.
Well, last comment is this tool that Manish presented is also super useful for the global setup. So I've been playing with the 2-degree version, and after Alper Manish put together these tools, it really streamlined the process of creating the files for the global. So it's not only useful for regional. So let's thank Manish one more time. We have 15 minutes break now. Okay, well, it's 10:31 Mountain Time. We are now starting with our second session of the day. And we have Abby Bodner that will talk about representation of surface mixed layer eddies affects the large scale ventilation on the global ocean. Abby, please go ahead and start the presentation.
Great. Hi, everyone. I'm sorry for not being able to be there in person. I'm going to be presenting work that's a collaborative effort by a few modeling centers, and the collaborators are listed here, where we're trying to understand the impact of the updated mixed layer eddy parameterization on the global circulation. So before I kind of get into the results, just a quick orientation if people aren't super familiar with the formulation. The mixed layer eddy parameterization, or submesoscale parameterization, represents the restratification effect by mixed layer eddies by slumping submesoscale fronts and effectively restratifying the mixed layer. It's cast in the form of a stream function, and it's found to have a very strong dependency on this frontal width parameter, which was previously suggested to be on the order of a deformation radius. But recently we proposed a new scaling, which relates this frontal width scaling to variables associated with boundary layer turbulence. So in particular, turbulent velocity scales coming from wind, stress, and surface cooling, as well as the boundary layer depth. Also, a new coefficient emerged from this new scaling, which in the paper we related to be on the order of a turbulent Richardson number of about 1/4. And it turns out that there are a lot of advantages of this new scaling. When you go back and put it into the form of the stream function, it removed sensitivity to an artificial parameter that was intended to avoid blow up near the equator, as well as introduced latitudinal dependency due to this Coriolis parameter and relationship with seasonality and atmospheric forcing. So there are a lot of advantages on its predecessor, and the work I'm presenting today is to try to understand the impact of an online implementation of this new formulation. Just a quick note on this coefficient, because this is going to turn out to be an important part of the story, is in the paper, if we follow the numbers of this turbulent Richardson number and the efficiency coefficient in the original Fox-Kemper parameterization, we get a new CR coefficient on the order of about 0.28. And I'll get back to this in a little bit. So in the paper, we kind of naively implemented it in CSM-POP. And the main idea was to show that there is some impact by changing this factor. And we found that there are certain regions around the world that are sensitive to this, and they're important for climate. But we kind of left all of the understanding of the impact of the climate as a whole to future work, which will be the focus of the results today. So using a framework developed by Takaya Uchida and collaborators, we compared the new Bodner parameterization and the Fox-Kemper parameterization to high-resolution simulation output where submesoscales are resolved down to a certain degree. And this is a useful framework because it can tell us what these coefficients should be. So it's kind of a reverse engineering type of approach where we use the actual stream function to then recreate what the fluxes should be. And it turns out that we were way off. We're about 3 orders of magnitude too high in this type of comparison. So the CR emerged to be on the order, oops, I lost my mouse, sorry, on the order of about 10 to the minus 3 compared to what we suggested. I should also note that the Fox-Kemper parameterization is about an order of magnitude too large, also based on this framework. The interesting part is that I'll soon present results from 3 different modeling centers that implemented the updated parameterization. But each one of these centers identified this as being an issue independently. So everyone kind of realized that the CR that we suggested in the paper was too large, and it resulted in a lot of wacky behavior. So Alistair pioneered the implementation of the new MLE parameterization in MOM6 and gave us the first GFDL MOM6 version. In GFDL, there's the ePBL boundary layer mixing scheme, which provides the parameters for boundary layer depth and the velocities. The mixed layer depth, which is this big H, is given by a filter over the boundary layer. And that's important because in the CSM implementation, that part is actually changed out to the actual mixed layer depth that's provided by the CSM model. Additionally, CSM uses a different mixing scheme, which I understand is being developed by Bill. We are also going to be comparing the results or contrasting them against a previous version of the mixing scheme by Ching Li in 2016, which incorporates waves. And then finally, Blom, the Norwegian ocean model, also adapted the MOM6 implementation. And in Blom, the mixing scheme is KBP. So the reason I'm kind of mentioning the mixing schemes is because these variables are coming from the mixing schemes. We're really seeing that there's a lot of sensitivity to the choice, to that choice that's made. So I'm showing some results. Wait, maybe before I do that, just in the favor of these models, this is still work in progress, and we're working on tuning to find the exact, the perfect CR, essentially. And also each modeling center uses a different approach for tuning, which will impact the criteria that I'm going to be showing next. So just kind of to put that in perspective. So this is the global mean ocean potential temperature. We're using the GRA force runs. Light colors correspond to the control runs, so the Fox-Kemper parameterization. dark colors correspond to the Bodner updated MLE parameterization. I have listed the different CRs that the different modeling centers have used. Each kind of version was attempted to come up with like the best, the best tuning possible. For CSM, which are the warm colors, I'm comparing against the two different mixing schemes, as well as in CSM, it turns out that a constant coefficient wasn't good enough. It kind of messed up a lot of the overturning circulation features. So in CSM, what they're currently doing is they've come up with this latitudinal dependency of this coefficient. And you can see here different versions that Gustavo's been trying. And the results that I'm going to be presenting today are based on this version 8, which is the dark blue line. So essentially what it's doing is it's reaching the GFDL level towards the tropics in the mid latitudes, and then it kind of tapers out towards the high latitudes. So in GFDL, this was actually the tuning metric, which provided kind of the ideal, the optimal CR, was trying to match the control over here. In Blom, they tuned against the stream function to try to capture the same stream function as the control, but we can see that there's quite a lot of similarity in the potential temperature. Whereas in CM, we see a widespread between the control. Sorry, I need to drink some water. Between the control and the new parameterization. Okay, this is mixed layer depth between, now I'm only showing for the new MLE, I'm only showing the kind of the best version that we have right now. So again, the light colors will be the control and the dark colors are the Bodner parameterization. And we're showing the 3 different modeling centers compared to observations, which is shown in black. So it's really hard to say which is better. And in some cases, we're getting closer. Like, for example, in the summer CSM, the new parameterization is closer to the maximum compared to the control. In other cases, it seems to be doing worse. So this is something that we're still trying to figure out. In this next slide, I'm showing a global map of this mixed layer depth difference. So this is the difference between the Bodner parameterization and results from the control Fox-Kemper parameterization. Upper panel is the GFDL model, middle panel CSM, and finally Blom. And this is global winter and summer in each model. So I purposely left the same color bar for all models so you can appreciate just the scale of differences between each one of the centers, which I found extremely interesting. The spatial patterns also differ. Some features that seem to be consistent are the summer equatorial region. We can see that there's more shoaling associated with the new parameterization, whereas there's a deepening in the higher latitudes. And if I compare to the Lee et al. Mixing scheme for the same type of, as a different control, we see even different results within the same CSM model. So even in the same model, there are different impacts of the MLE parameterization if we just change the mixing scheme. We're interested to understand how this impacts the ventilation of the global ocean. So as a proxy for that, we've been using Ideal Age Tracer, which tells us about the relationship of a certain body of water to the last time it touched the surface. We're comparing to depth, 100 meters, which represents kind of within the mixed layer, and below the thermocline at 1,750 meters. What we're seeing here again is the difference between the Bodner parameterization results and the Fox-Kemper parameterization results. And again, the 3 rows are the 3 modeling centers. So at a glance, they look very different. We're seeing different behavior in different models and in different spatial patterns. So one thing that's similar is that around the Southern Ocean, we're seeing older water, which means that there's less mixing. if I'm interpreting that right. So there's shoaling, and there's older water kind of closer to 100 meters. Whereas if we go down in depth, the models disagree, and this might have to do also with how long we ran the models for, but we are seeing older waters at depth at GFDL, but then CSM and Blom, for example, show that there's younger water at depth. So this is hinting that the overturning circulation is changing, and that's in fact what we see. So I'm showing here differences in AMOC between the Bodner runs and the Fox-Kemper runs. So GFDL is showing a weakening in AMOC, whereas Blom is showing a strengthening in AMOC. CSM is showing maybe both in different depths. And if we look at compared to a different mixing scheme within CSM, we see a complete opposite effect, which is really interesting. Just as a teaser, we're doing a complementary effort in NEMO where we're implementing a CNN neural network that infers submesoscale fluxes. So in an offline approach, we found that the CNN predicts, quote, better submesoscale fluxes. And the question here really is, do better fluxes result in a better GCM? The approach that they're taking is, in Juliana Sumer's group, is that they're inverting the stream function from the predicted fluxes. And there's not a lot to report in terms of results just yet, except that I'll note that we're finding kind of very similar problems in terms of the Southern Ocean. The circulation around the Southern Ocean gets wacky, and that just leads to the whole model to behave differently. So there's a lot of relationship in terms of the effort that we're trying to combine here. So conclusions, or maybe lack of conclusions, is that MLE is still a very important tuning knob. We're finding that it's a huge control on the global circulation. The new parameterization infers stronger fluxes, which means that we had to tune it down a little bit in each model in different ways to avoid unexpected errors. The impact on the global circulation patterns is different in every model between GFDL, CSM, and Blom. And due to the new relationship with boundary layer turbulence, it's making the MLE parameterization even more sensitive to the choice of parameterization. So whether we're using KPP, EPBL, with waves or without waves, that's all impacting how the MLE responds. And it's not really clear yet what the right answer is or what's the best way to tune these two together. And a lot of this is hinting at more work that's needed to determine the optimal CR coefficient, which if we also go back to the original paper, that really hinted at the relationship between submesoscales and boundary layer turbulence. So it's really controlling that relationship. So well, I'll finish, and a lot of collaborators are in the room, so if there are questions, hopefully I can ask for help.
Thank you so much, Abby. Thanks for joining us. Any questions for Abby from the room first?
Yeah, I wish.
Bill?
Yeah, Abby, do you know what is happening with, as far as the wave part in that denominator with the W star and the U star? What's he actually doing, and how far has he gotten?
Are you asking how W star will change with the waves?
Well, you said that, I think it was Qingli was working on that. I'm just wondering how far, if you know how far he's gotten, and how is it going to work in that? Is it a separate term, another coefficient, or how he's implementing that? What he's using?
I think it's already implemented, right? Because we're using the scheme. So I think it amplifies.
Okay, somewhere it is. Okay.
Yeah, I think it amplifies U star in CSM. Is that correct? I see people are nodding.
We interpreted it that way, yes.
But I don't think it's fitting back to us, to at least CSM, right? That W star, like when we have waves.
Yeah, it's different. Yeah.
Might somewhere, I don't know.
I don't remember that I think the only.
Oh, okay, thank you. That we'll have to look into that, see whether it's already there or not. Yeah.
Any other questions, Justin?
Abigail, very nice talk. I had a question about whether you are improving the mixed layer depths, and you showed that kind of zonal mean plot. And my point was just, for example, in winter in the Southern Ocean, I think you won't be able to improve certain biases, or they might relate to other factors which you're not controlling with your submesoscale. And one example with pop, indeed, the general mean circulation had problems which affected the stratification. So, yeah, in some cases, I think it's you won't be able to hope to improve it drastically because of other errors.
Okay, that's helpful. Thank you.
Bob?
So if we go to your conclusion, you have two bullets, one at the beginning and one at the end, which basically explains why we're stuck on the horns of a dilemma. First, this is an amazingly powerful knob for tuning the overall performance of climate models. And in particular, it's one of the things that we can use in the ocean to fix problems that are coming from the atmosphere. On the other hand, you're working hard to turn that from something where we say, well, it's sort of like this, but we can tune it because we don't know what it is, into something where you say, but Abigail says it should be exactly this number based on careful theoretical studies. If you take away our tuning knob, can you give us a different one that's as effective?
So actually, like, we didn't determine it explicitly. It's, O of, so that could be interpreted as something that you can tune, but maybe it needs to be better bounded than it currently is. That's one way to think about it.
We only used maybe a dozen LES that were coupled for the fitting. And I think we probably needed about an order of magnitude more LES to get a really good handle on what CR should have been from a theoretical perspective.
Yeah.
But those are expensive.
So is CR a global constant, or?
Yes. I believe it's universal.
Or should it vary spatially?
We are very spatially.
It should be universal. The F upstairs is supposed to take, and the H is supposed to take care of all the local.
If it didn't screw things up, we'd be constant. But again, how many other errors are you making up with this thing?
Absolutely.
Well, not just the atmosphere, but there's other ocean problems too. I mean, so we're just not sure. If you look at that one thing we were using, it's because the mixed layer depths in the recirculation zone of the Gulf Stream and Kuroshio were just too deep. So one way of fixing that is to stick this restratifier in there. Well, that might not be the right thing to do. So it would be useful to get some idea from those that put this in where they're really confident. What regions of the ocean they're more confident in and where they're not, so that the spatial and temporal variability that the scheme gives is valid. That would be really useful to know where you're more confident than other places.
Yeah,
And maybe
on
we
that
wouldn't
note,
be able to change things that much there.
one of the early slides from Takaya, it was a way to diagnose CR offline, but I think focusing on a single region, right? Like it was the North Atlantic.
It was the motor order region of the Gulf Stream recirculation. It was exactly where he was looking.
Does it change if you look at different regions? If he repeated his analysis for a different region, would you still get the same CR? So that's one thing to check.
Yeah. Different atmosphere. And also those models, some of the models that are going into that CR calculation are kind of moderate submesoscale permitting. So I think we're also pretty limited on those truth runs as well.
Yeah.
All right. Well, thank you so much, Abby, one more time.
Yeah, thanks, everyone.
Matt, are you there? Yes, I see you. Yeah. Okay, so please go ahead and share your screen. Our next speaker is Matt Pujji, and he will talk about isopeakinal tracer mixing via an energy backscatter parameterization.
Cool. Can everyone hear me okay?
Yes, we can.
Okay, great. Thanks. So, yeah, today I'm going to be talking about my current project. I'm a PhD student at NYU working with Schaefer, Smith, and Marzana. and I'm going to be talking about isopycnal mixing and backscatter parameterizations in eddy permitting ocean models. And all the results I'm going to show are quite recent and very much work in progress, so any feedback I'm keen to hear. So I'll first talk about parameterization at coarse resolution to kind of motivate the eddy permitting regime. So there are two main parameterizations for mesoscale eddies at these sorts of resolutions. There's the parameterization of the effective transport, which is often done by the Dentmik-Williams scheme, which models the baroclinic instability-induced conversion of a mean APE to eddy kinetic energy and the eddy-induced transport that will occur during this slumping of isopycnals. And in Z-coordinate models, this can be encoded as an anti-symmetric tensor that acts, enters both the buoyancy and tracer equations and acts on buoyancy and tracer gradients, respectively. It requires of the modeler to prescribe this kappa GM, which is like a thickness, a diffusivity of isopycnal thickness, and GM is necessary to get the mean stratification correct. The other kind of main parameterization that's used is to parameterize the enhanced dissipation of tracer variance that occurs through eddy as a result of eddy stirring, and this is often done using what's called the Reddy scheme, which takes diffusion in the local isopycnal plane and then rotates it back into the Eulerian frame. And this S matrix is a symmetric matrix. And again, it requires the modeler to prescribe a diffusivity, this kappa R, which is the isopycnal tracer diffusivity, or the tracer diffusivity in the isopycnal plane. And importantly, Reddy has no effect on stratification, as it acts only in the isopycnal plane, but it has a big effect on tracer distributions as well as surface uptake. And historically, I think kappa GM and kappa R have been set equal to each other, and there are some theoretical arguments for why they should in fact be different, but
or the same.
all the same. And then the prognostic equation, the resolved tracer, includes these parameterizations as such, and you can see that AGM and SR can be added together into one single mixing tensor that then acts on mean tracer gradients. But when we move to sort of eddy permitting resolutions, these two parameterizations were kind of developed when models didn't resolve any of the mesoscale turbulence, whereas now global ocean models are beginning to enter new regimes where horizontal resolutions are such that some of the mesoscale turbulence is resolved and maybe only over parts of the domain. And this is often termed the eddy permitting or gray zone regime. And so we have to reevaluate the old parameterizations as they might no longer be either necessary or applicable in this new regime. And so when horizontal resolutions are said to be eddy permitting, the horizontal resolution is often close to the local deformation radius, meaning that the dissipation scale from the hyperviscous dissipation starts to push into the eddy scale. And this results in spurious energy dissipation at the grid scale and consequently less energy at all scales. And so I'm demonstrating this idea here on the right from a study which performed a suite of two-layer QG simulations where the horizontal resolution was systematically decreased. And as the resolution became coarser, the whole barotropic energy spectrum, which I'm showing, was impacted because of this idea I've just described, that grid scale dissipation is cutting off the energy source for the inverse cascade. And what Janssen and Held proposed is that the hyperviscous dissipation could be combined with a negative viscosity that then re-injects energy at larger scales, and this is to represent this expected energy backscatter from small to large scales. And you can see that this by and large works quite well for the energetics, where the whole energy spectrum becomes elevated to match the high-res truth. This idea has since been taken up with more realistic primitive equation setups, where the magnitude of this negative viscosity is set using an estimate of the local subgrid kinetic energy by solving a prognostic subgrid KE budget. This budget might have the effect of GM as a source because GM implicitly models the conversion of mean APE to subgrid kinetic energy, as well as the hyperviscous dissipation from Smagorinsky viscosity as a source. And then backscatter to the resolved scales is a sink of subgrid kinetic energy as well as dissipation and advection. Recently, a study led by Elizabeth Jankowski in using this sort of setup showed that optimal backscatter parameterization at 0.5 degree, in fact, turned off GM completely. And critically, they had to use a surface intensified vertical structure for the negative viscosity. And they showed that this could get both the domain average kinetic energy and the domain averaged APE correct with respect to the high-res truth. So this means that the re-energized eddies are relaxing the isopycnals themselves without any additional GM. But the question of whether these re-energized eddies are also doing enough isopycnal mixing, meaning that any additional ready is also unnecessary, hasn't really been answered with a dedicated study. So specifically, the idea is that if GM is suggested to be turned off at these eddy permitting resolutions with a well-tuned backscatter parametrization, then does this also imply that ready should be turned off too? So this, just as I said, this is kind of the hypothesis that we wanted to test, that this backscatter parametrization from Jankowski et al. Is also replacing the need for any additional ready diffusion. And I'm testing this hypothesis by running a backscatter parametrized simulation with no additional ready diffusion and assessing whether there's sufficient stirring of traces by the parameterized eddy field to get the tracer distributions right with respect to the high-res, with respect to a high-res truth. So I'll just describe the model setup that I'm using. This should be quite familiar to many of you. This is solving the adiabatic primitive equations in a double hemisphere single basin domain. It's forced by a constant in time and zonally constant wind forcing at the surface, and there's no buoyancy forcing and no diapycnal mixing. So this is specifically, this is the Neverworld 2 configuration in MOM6. It's got 15 isopycnal layers, effectively solving the stacked shallow water equations. There's topography throughout the domain. There's a periodic southern channel that's meant to represent the ACC. And I'll talk about these two resolutions, 0.5 degree, which is sort of the upper limit of what can be considered eddy permitting, and high-res 1/32 eddy resolving truth. And the parametrization that I'm using is the backscatter with the surface intensified backscatter with no GM from Jankowski et al. And then the new thing I do here is that I do these runs with passive traces advected online by the model, and in particular a set of passive traces that are slowly restored to mean target gradients, which I'll discuss in a few slides, against which these traces eventually reach some force dissipative equilibrium. And then the analysis that I'll describe is over this 500-day window in gray at the end of this time series. And the backscatter parametrization is tuned to match the kinetic energy and the APE of the high-res coarsen to 0.5 degree. So I now showed the kind of time mean tracer distributions for one of these traces. So this is a 500-day mean of a tracer that's restored to a sine X gradient on layer 5, which is it's at about 500 meters in much of the interior and outcrops in the Southern Ocean. And what I claim is that indeed the backscatter parametrized simulation is getting the tracer distribution largely right with respect to the 1/32. The fact that it's largely correct is consistent with the energetics being largely similar between the backscatter and high-res simulations, which I'm showing in the top right. And note that this is on a log scale. But rather than using this sort of I metric, I now want to be a bit more precise about estimating the strength of mixing in these simulations. So to do this, we can consider a flux gradient relationship for the traces, where the mean eddy fluxes are equal to some mixing tensor K times the mean gradients. And because we're in an isopycnal model, these means are done using a thickness weighted average, which I denote with a hat. And then prime terms of the eddy deviations. And then note also that this matrix is 2 by 2 because there's no diapycnal mixing in our simulations. And in general, the elements of this tensor can vary in space, meaning the mixing is varying in space. Specifically, the averaging I'm using in this thickness weighted average involves an online time average over the 500-day window and an offline coarsening onto 2 degree by 2 degree boxes. And the objective here is to back out some estimate of the mixing tensor K, given the mean eddy fluxes and mean gradients in our model. So the method I do should also maybe be familiar to some of you. So this is what's known as the method of multiple traces. It's been used in both atmospheric and oceanic contexts and has shown good skill at estimating mixing tensors. So I'll describe how this works. So what we do is we advect a set of n passive traces by the same flow and slowly restore these traces to some target fields. Here, these sine x and y gradients, so that then the traces reach some statistical equilibrium with mean gradients. We can then write the flux gradient relationship for each tracer, Cj, all with the same mixing tensor, which you can then combine into an overdetermined matrix equation. This G transpose K transpose equals F transpose, where the columns of G are the mean gradients for each tracer and columns of F are the mean fluxes. And this is overdetermined, so the optimal solution is simply the least squares solution, which is then our estimate for the mixing tensor. And the idea is that because we've used information from many different tracers, this mixing tensor should largely be an indication of the intrinsic mixing done by the flow and can then, in theory, be applied to traces not included in the inversion. And specifically, the results I'll now show, I'm using 6 traces using these 2 gradients with 3 different relaxation timescales, 2 years, 4 years, and 6 years, so that then the equilibrated gradients are always slightly misaligned, so that they're always linearly independent and the inversion doesn't fail. So I'm going to focus on the symmetric part S of this mixing tensor in contrast to the anti-symmetric part A, as it's the symmetric part that contributes to irreversible mixing, which is what Reddy intends to parameterize. And since S is symmetric, it can be orthogonally diagonalized with its eigenvalues kappa 1 and kappa 2 representing isopycnal diffusivities in 2 orthogonal mixing directions. And I'm showing here on the right maps of the larger of these diffusivities on that same layer 5, which I showed the tracer distributions earlier. And you can see that, again, consistent with what I showed before, the estimated isopycnal diffusivities are largely similar in both spatial structure and magnitude between the backscatter and the high res. And I'm showing also the unparameterized run on the left, which has substantially less mixing. And note again, all of this is on a log scale. You'll also see that there are occasionally negative diffusivities. And this simply represents where advection of tracer variance can cause locally up gradient fluxes. And in the title of each plot, I've given averages of kappa 1 over this black box in the southern part of the domain, over only the positive values. And in fact, the backscatter run sometimes has larger magnitude diffusivities than the high res, which is interesting. And this might be related to differences in the eddy length scales between the 2 runs, even though they have the same eddigetics, but making a sort of mixing length argument there. But despite this, if you take global means of the average isopycnal diffusivity, so the average of kappa 1 and kappa 2, you can see that the backscatter simulation is very close to the high res. Taking a look now at the zonal mean structure of these diffusivities, you can again see that the backscatter simulation and the 1/32 have fairly similar spatial distributions of mixing. However, the mixing tends to be weaker at depth in the northern, I'm just trying to get my mouse, the northern hemisphere than in the high res, and also slightly lower in magnitude in the over depth in the southern channel. But you know, by and large, it's doing a pretty good job. Just to further demonstrate what this mixing tensor estimate is actually doing, I can show that the mixing tensor can reconstruct mean eddy fluxes from the mean gradients. So I'm showing here a flux reconstruction using one of the gradients that was included in the inversion. So this is verifying that the errors in the mixing tensor are small. So panels A and D are showing the eddy fluxes diagnosed directly from the model. And then panels B and E are the reconstruction using the mixing tensor and the mean gradients. And if I plot PDFs of the relative errors between these two over the whole domain, you can see it's indeed concentrated close to 0, which is good. We can also show that the mixing tensor reconstructs fluxes for a tracer not included in the inversion. So I'm showing here this tracer that's restored to the mean depth along each isopycnal layer. So there'll be gradients wherever the isopycnal slope. And again, I'm showing the fluxes diagnosed from the model, and then they're reconstructions using the mixing tensor and the mean gradients. And then again, also the PDFs of the relative errors, confined only to this southern part of the domain where the eddy fluxes actually are. And the errors are slightly larger, but still concentrated close to 0. So this is verifying that the mixing tensor estimates we've made are largely reflections of the underlying strength of mixing by the flow and not tied to the particular traces that we've used in the inversion. The last result I wanted to show, which is some fairly recent runs I've done, looks at the uptake of a surface dye tracer. And so this is fixed at 1 whenever the mean layer depth is smaller than 100 meters and is otherwise passively advected into the interior. And on the left, I'm showing this dye tracer on this same layer 5, which is also the first layer to outcrop in the southern channel, and is otherwise at roughly 500 meters depth. And these are snapshots of the dye after 500 days in the half-degree simulations. I haven't been able to do the 1/32 degree yet. And you can see that the tracer front is much more diffuse in the backscatter case than the unparameterized case, which is indicative of more energetic stirring by the flow. And then if you look at the area average concentration on this isopycnal, there's a roughly 13% difference in the relative increase in concentration from over the 500-day period between the unparameterized and backscatter parameterized. So yeah, I haven't yet been able to do this with the 1/32, but given that I've shown that this backscatter simulation is showing fairly similar mixing to the 1/32, I'm expecting that the uptake of this dye tracer to be similar in these runs, but of course this needs to be confirmed. So yeah, to summarize, I've looked at isopycnal mixing of tracers in a half-degree simulation with backscatter and with a backscatter parameterization and no GM already. And by and large, the backscatter parameterization is energizing the resolved eddies sufficiently strongly to induce isopycnal mixing to match a high-res truth, where the eddies are almost completely resolved. And the isopycnal diffusivity is estimated using the method of multiple tracers. Backscatter parameterized run is also showing an elevated uptake of this surface tracer than the unparameterized simulation. So where I'm going with this currently, I'm looking at comparing a 1/4 degree unparameterized and backscatter parameterized, which is also probably a fairer comparison since often 1/4 degree global simulations are run without any mesoscale parameterization currently. And I also need to look at other metrics to assess where backscatter is getting things right and where it's wrong. So yeah, thanks. I'm keen to take any questions.
Thank you, Matt. That's great. Questions from the room. Baylor.
Hey Matt, this is really great. I'm amazed that you've gotten inversion working as well as it is. It's a very finicky process, so that's excellent. You didn't show any results from the second eigenvalue, which I often think is the more direct one to the ready tensor, because the first one is normally shear dispersion, and then the second one is the cross front dispersion, mostly. Did those results look as good?
So yeah, I somewhat varied this because with what I showed here, because with these particular gradients that I used, if you look at kappa 2, they tended to be a lot more negative values. And so I'm currently redoing the runs with more spatial gradients, and I'm fairly confident that that's going to remove some of those negative values. But yeah, they tended to be about 3 times smaller magnitude than the kappa 1 and kind of more homogeneous across the domain, but they're also tended to be more negative values, which I was finding hard to interpret.
Would the backscatter also improve those?
Yeah, it was like same order as the 1/32, and yeah.
Any other questions?
I got a question.
Sorry, Jason.
So you've done this in a simplified model with simplified geometry. So how confident are you that these will hold up in a realistic global ocean model with a full equation of state?
I missed that last part, a full equation of state.
Yeah.
Not totally. So I know that Wenda Zhang, who's working at GFDL, he's looking at quarter degree global runs using backscatter and no ready, and I think he's seeing results that are somewhat consistent with what I've been seeing, that it's doing getting a lot of the mixing right and might sometimes be doing too much mixing. So I guess I'm tentatively confident that the results are kind of similar in how they port between this idealized case and the global runs, but I'm not sure about any of the other results.
Okay, any other questions online? No, let's think back one more time.
Thanks.
So our next speaker is Yao Gahonzu. That will talk about a weighted, essentially non-oscillatory tracer advection scheme in MOM6. Thanks for joining us, Yao.
Weighted essential non-oscillatory tracer advection scheme in MOM6, and I'm doing this work with Alan Overcraft and Eric Chassinier here at COOPS. This is still a work in progress, and the main goal for today's presentation to talk about what I've been doing on implementation of the Ueno-based solver for the tracer in MOM, and also present some initial evaluation of that scheme versus against BPM, which is the current Ueno current tracer advection scheme for the tracer in MOM6. So the motivation of this work is as we know, the PPM is lower order scheme, which is a third order scheme, and we know that the lower order schemes are often numerically dissipative. So we're trying to provide some higher order methods that can be more accurate and at the same time less dissipative. And so if we are choosing that numerical scheme, which is higher order, we also need to show that, or to make sure that can solve some discontinuity problem and avoid some numerical oscillations. And Ueno schemes, which is reconstruction, proved to be can solve that problem. The drawback of higher order can provide some higher order accuracy, at the same time handling very well the discontinuity near the sharp gradient. So without necessarily generating any superior oscillation on. So in MOM, there's a different type of tracer, and as we know in ocean in general, there's different type of tracer. We have passive tracers and then the active tracers. And the passive tracer the tracer does not affect the circulation of the ocean, and we can see some dye tracer and biochemical tracers. And active tracers are the tracers that mostly affect the circulation of the ocean or the momentum equation. And we can see, for instance, the temperature, the salinity, and all that. So if you want to know more about the tracer in MOM, you can look at the documentation on their documentation page. So back to this, my work is an overview of the Ueno schemes. And generally, if you consider just simple 1D advection equation to break down how the things work. So you saw this in time and the space, and you're trying to find these fluxes, which fluxes like inside this cell. We need to find the flux computation when the tracer is moving from left to the right. Then we need to find this flux reconstruction here at the left and the right in order to propagate the tracer in space. So we're not looking at the time solvers, but we are looking at the space solver, which is high order method. And so far in MOM, we have implemented the 5th order, 7th order, as well as the 9th order scheme, Ueno scheme that we are currently testing. And so why Ueno? Ueno is dynamically, for instance, if you want to, if you like 5th order Ueno scheme, we need to reconstruct, we consider 5-point stencil, which consider this I-2 to I+2. And what Wino does to consider lower order, we consider lower order schemes, and then use what we call, then dynamically approximate those with lower order schemes, and then reconstruct that using a nonlinear weights. And the good things about the Wino scheme is that you can, once you have those lower order polynomial, you can combine them using the nonlinear weights. And in the smooth region, the scheme provide like a higher order, high weights, making the solution more accurate in the smooth region. And then in the near the discontinuity or the sharp gradient, what it does to reduce those weights so that the scheme can be also accurate, but at the same time capture that discontinuity and be stable at the same time. So so that's what it is. So in the high in the front of small region, and we have a high order accuracy because we provide more high order weights, nonlinear weights, and then in lower order schemes, they decrease the lower order in order to have more accurate result in near the discontinuity. So this is what we have done so far, and here, so by default, Wino is not monotonous preserving because, for instance, if you look at the salinity or salt content in the ocean, so in case you have negative salt, is not. So we need to make sure that that scheme is monotonic, and by default, the Wino scheme is not monotonic. So what we did is to bound the flux we computed. So if you computed the flux at cell H I+2, then we need to bound that reconstructed flux to be within the minimum and bound. So we consider the initial evaluation or reconstruction of the flux, and then we modify that using the MT, which is as follows. So we find the minimum and the maximum of that flux that we call U min and U max to bound to that flux we considered. So we use this approach, and that being developed by the Shu and her in their papers. And once we have these values, what do we do to bound these original fluxes? Flux we consider using this minimum, which add as a limiter to that. So by doing so, we avoid having negative pressure concentration, and at the same time, we also avoid having some numerical oscillation. Okay, so I don't know if this can play. No. This is a movie, but it's not playing.
Oh, it's not playing.
Yes. So if it's not playing, so the rest is going to be the same.
Maybe if you go out of presenter mode.
Yeah, do you want to try to go out of presenter mode and see if it plays?
Yes. So I have it play on my local system, but since I'm presenting from the Google Drive, I cannot. So the movies are not in the Google Drive. Anyway, so what I'm presenting here, the previous result is this wanted to show, first of all, that if you consider different wave configurations or tracer content, there we have 5 layers, where each layer contains different tracer configuration. We have the square, the triangular, the cosine, and the cylinder and the cos cylinder. And this is to consider different configurations so that the Wino scheme, to make sure that the Wino scheme is working. And as I mentioned, this little caption here is that the scheme is stable and less distributive. And if we compare that with the ppm, which is on the left, and then we have Wino 5 and Wino 7 here. So we do that, and we ran this for 2 days. We have like 1.2 kilometer visualization, and then we also have 2.4 gigabit visualization. And we clearly see that the Wino 5 and Wino 7 are performing well in terms of numerical dissipation. They are less dissipative. The same thing goes for when we go for the lower resolution. So to make sure that everything is working, we also run for different grid configuration, which is on curvilinear grid, to make sure, because as we know in real application, the grid are not always uniform. So we also run this on the curvilinear grid, and we show that the Windows 7 is doing well in terms of reducing the numerical dissipation. So we also run this on more simple but realistic context, where we consider double GI test case, where we prescribe the passive tracer in the top layer, and we run this for 5 years, and using like 4 km resolution with all the wind stress in the Coriolis. So we also show that this, as the wave the things run, we still have like lower numerical dissipation in the Windows 7, which prove that the scheme is actually good in terms of numerical errors and accurate. So we also, so far what I presented were mostly on flat bottom topography. So we also consider different bottom topography, which is we have a dam break where we have like dense water on the shelf, and inside that dense water we prescribe a tracer, passive tracer again, and we let that dense water flow down. And what we did was to make sure how does that tracer dissipate. So the comparison between the PPM scheme on the left and the Windows scheme shows that the Windows scheme is still doing well in terms of numerical error and dissipation. And if this is not also plain, but if we look at what we did for the right animation is to draw a line through the middle of this, and we see that as the time goes on, we can see that the tracer concentration is higher in the Windows 7 scheme. So those are just simple, like more of idealized test case where we run those test cases more idealized. This one is more of a realistic application where we run this on full configuration, where we have open boundary, and also we have all the external forcings and wind and all of that. And we run this is like more realistic application. And what we did was to prescribe a passive tracer, and we ran this for using 41 layers, and for only 1 year. We compare PPM versus Windows, and we prescribe passive tracer on the top layers, top 8 layers, and then over there you can change. We have a test concentration equal to 100, and we run this for 1 year. And from that observation, if the movie is not playing, but we also see that the Windows scheme is doing well in numerical dissipation, and we can clearly see some differences in showing that the scheme is actually working and stable. So although I don't have movie to show how things look like in reality, but in summary, we have tested the Windows-based solver transport in MOMSIS, both on idealized test case and the realistic, as I showed over the Gulf. We clearly see some improvement in the model result. At the same time, we can see that the scheme is stable and reduce numerical dissipation. So the next step is we are still testing the Windows Solver on more realistic applications, since we have already done those idealized experiments. So we are running more complex that. So once everything check out and we clean up the code, we'll be submitting this to the NOAA DFDL MOMS main branch for release. So I would like to thank you.
Thank you, Yao, and sorry for the technical issue with the movies. Questions from the room first?
I have one quick one. Yeah, this is a one-dimensional implementation of Wino in the horizontal like coordinates, not the 3D one with the Riemann fan and all of the extra stuff that they do in Wino.
So MOM initially do like directional splitting. So if, for instance, in 2D or 3D, you do reconstruction on S and Y direction. So we are following the same steps where we have like we know reconstruct over the S direction, over all the directional, and then combine that. So we don't have like fully 2D or 3D window scheme, but we have like each one dimension, but with the directional splitting.
Thank you.
Yeah.
And just to follow up on Baylor's question, this is using the pseudo compressibility exactly the same way as the PPM scheme is, I believe.
Yes.
Okay, so for different tracers, we could use Wino for some and PPM for others without there being too much complication?
At the moment, once you decide to use PPM, like in a tracer, you can use either PPM or Wino, right? So initially we have PLM, PPM schemes in. So if you decide to use one of those solvers, then you are using that in the simulation. So in the same way, if you want to use Wino, so we are using Wino for salinity, temperature. I don't know if that's what you are referring to.
Okay. So that, just to follow up, so that's how the code is written, but is there any reason why we couldn't choose Wino 7 for some tracers and PPM for other tracers? They're broadly compatible schemes in that sense. Is that okay? Thank you.
Yes.
Okay, one last question. Peter?
So is this scheme much more computationally expensive?
That's a very good question. I have not looked into that yet because I'm mostly on getting things to work, make sure that everything checked out before I look into how expensive it is.
Okay, thank you so much, y'all. Let's think y'all one more time.
Thank you.
Probably maybe you could work with them getting the movies to put links for the.
Yeah, that's a good idea.
So
Now, if you can send me the movies, we can put it on the links and at least have people watch afterwards on the
Yes, I will do that.
website. Yeah, thank you.
Thank you.
Okay, so the last talk of this morning is by Ian Grooms, and Ian will talk about designing a high common grid for CSM MOM6.
Should I stand
Yeah,
here?
it's good. Fine. Can you hear online if Ian talks from here? Can you give us a thumbs up?
Sounds like the mic
Oh,
is
there's
working
a
in the
mic.
room.
Okay, yeah, never mind.
Yeah.
Thank you.
Yes.
Okay. Shall I get started? All right. So, a year ago at this meeting, we discussed and decided to use the HICOM 1 coordinate in MOM6 for CESM 3. We had been evaluating that and the CES and the Z-star coordinate. So I'm going to quickly review how does HICOM 1 coordinate works. So you pass in 3 lists. Really, you only need 2 and you can do as many as 4, but I'm only going to talk about 3. The 3 that you need to give are a list of Z-star target depths. There's an asterisk there too, but you give it target depths, and then you give it interface target values for density, and it's sigma 2. I'm going to call those sigma k, and then you can give it max layer thicknesses. Okay, so you've got those 3 quantities indexed by layer index k. It starts at the top of the ocean, so the top interface is always just the top surface, wherever it is. And then it works down and finds the interfaces one by one from top to bottom. So if you're at some interface, you know where you are, you're looking down to find the next one, you find 2 depths. One of them is the depth of the Z-star interface from the list. The other one, you find the next isopycnal target in the list and you find the depth of that interface. And then you pick whichever one is deeper and you use that. Unless the distance from where you are now till the next one you chose is too thick, and then you bring that interface up a bit until it reaches the maximum thickness. So that's how HICOM 1 works. We have a HICOM coordination configuration that we've been using, 75 layers. We're pretty happy with it. No real change it. It works for our global current sort of climate simulations. But as we've already heard, we have other configurations that we're interested in doing in CESM. Now, last glacial maximum and other climates, future climates. We also want to do regional configurations. For example, if you want to do a regional Arctic configuration and you use our current
HICOM coordinate, it's just going to be z-star, right? Which is not optimal. So we want to be able to configure the grid for these different climates or different regions. So how did we configure the existing grid, or how have other people configured their existing HICOM 1 coordinate? Well, they've done it by hand. There's not a systematic way of doing it. And that's not a bad thing. You can do a really good job by hand. I mean, the one that we have, we like. The one that is in OM4, I think, is a good one. I don't want to criticize those, but it's effort to develop these things by hand. And if you have to go through and do it by hand for every single new configuration, it's a lot of work. So I want to avoid that. And that's what this talk is about. I'm going to start where my own interests started, which was trying to choose isopycnal targets. And then I'm going to come back and think about, well, also we need to think about the Z-star targets. So I want to introduce some concepts here. The first concept is the figure on the right. This is a grid density function. It's not density like potential density or in situ density, it's grid density. So the plot on the right here, the x-axis is depth. The right is the top of the ocean. I have two grid density functions. The blue one is uniform, and with that you get an equispaced grid. And the red one has higher density near the surface of the ocean, higher grid density. So if you use that grid density function, you get close points that are more closely spaced near the top and points that are more widely spaced near the bottom. Now in practice, how you actually use these to construct a grid is not hard, but for the sake of time, that's the figure on the left, but for the sake of time, I'm going to move on. So I'm going to frame this question as, what is a good grid density function? And the picture here is the grid density function is a function of z, but I'm actually going to be interested in a grid density function that is a function of sigma 2. Okay. Another bit of a digression here. So I introduced grid density functions. I'm now going to talk about a different coordinate entirely, not the HICOM 1 coordinate at all. It's a coordinate that we call the Charney coordinate. It was introduced by Charney in his, at least that's the earliest that I know of, in his 71 paper on geostrophic turbulence. And in differential form, the Charney coordinate R is related to the Z coordinate by the stratification, N of Z. So you can show with a WKV analysis that baroclinic modes are basically cosines in this coordinate with an amplitude modulation. And as a result of that, I showed with a student who graduated last summer, if you use a grid that is equally spaced in the Charney coordinate, you do almost an optimal job, a near optimal job of resolving baroclinic modes. There's other reasons for thinking that an equispaced grid in the Charney coordinate is a good idea. We're not going to use the Charney coordinate, of course, because it's not in MOM6. That's, maybe one day, but certainly not now. But I want to use the grid density function that goes with this coordinate. So you could say, what if my isopycnals were all flat? Then an equispaced grid in the Charney coordinate corresponds to z levels. Those z levels have some grid density. What's that grid density function? It's actually just N of z. It's just the stratification, the buoyancy frequency. So if you give me, a discrete density profile, so I've pulled from the Tropical Pacific World Ocean Atlas here, a sigma 2 profile, that's the blue line. I can, from that, construct the corresponding grid density that corresponds to an equispaced grid in the Charney coordinate. And then from that, I can give you either equally spaced points in Z that corresponds to equally spaced points in the Charney coordinate, or I can give you points in sigma 2 that corresponds to an equispaced grid in the Charney coordinate. And that's what I've shown here. Actually, the vertical lines are an equispaced grid in the Charney coordinate, but they're sigma 2 values. There's 15 of them. And then the horizontal lines are Z values that correspond to an equispaced grid in the Charney coordinate. And I can do as many as I want. The way this works, once you have the density function, you can put as many points as you want in a self-consistent way. I did 15 because it's easier to see. Okay, so what I've just shown, I can download World Ocean Atlas or whatever database, and every column of fluid gives me one grid density function. But what I want is just one grid density function that I can use for the whole globe. So I need a way to combine all these grid density functions before I can actually use it for HICOM, for the HICOM coordinates. So here are now 3 density profiles on the left. The green one is from the Baltic. These are all World Ocean Atlas. It's very shallow and very light. The blue one is the one I just showed you from the tropical Pacific. The orange one is from the Arctic. It's, you know, medium depth here and quite a bit more dense values. On the right, the green, blue, and orange lines are the grid density functions as a function of sigma 2 for each of those 3 profiles. And I need to combine them into one, and I'm just averaging. Okay. In practice, later on, I'm going to do a percentile. So at any given sigma 2 value here, you have a bunch of grid density values, one for every column of fluid in the domain. And so you have a bunch of values, and I just take like the 98th percentile or something, right? But for this plot, I've just averaged them. So the red line is the average. And then that's one grid density function. And I can use it to create layers or interface values. And that's what I've shown on the left. If you average, these are 15 interface values in that grid density function. Some of them are in the Baltic, some of them work for the Pacific and the Arctic, but they cover the whole range. So I'm just doing averaging or, you know, quantiles right now. I would, if I had more time, maybe in the summer, I'll work on different approaches for taking the global data and condensing it down, maybe clustering or something like this, but I haven't done that yet. So I've done this with the World Ocean Atlas monthly climatology, the 1 degree product. I actually don't use an equispaced grid in the charting coordinate. I surface intensify it. And there are reasons for that related to SQG type behavior that I won't go into for the sake of time again. Also, it helps resolve the main thermocline. Instead of just averaging all the grid densities, I take the 95th percentile or the 97th percentile or something like that. What does it produce? So here are the sigma 2 target values on the y-axis as a function of layer index K. The blue line is what we're currently using. The yellowish line is what OM4 is using, and the red line is what I've produced. And so my values are pretty close to what we're currently using in MOM6 in CESM, and I think that's a good thing because we liked what we already had, right? The main goal of this is not to change what we have now, it's to develop a tool that will automatically predict something that's very similar to what we have now in the current climate, and then when we use it for different climates or different regions, we hope that it will be giving us something that is also good. So that's how I've done the sigma 2 targets, but it's not an isopycnal grid. It's not an isopycnal model, it's a hybrid model. And the other parts of the coordinate matter a lot. So as I was playing with this and tuning these things, I realized how important the Z-star part was. And so I decided to come back and revisit that as well. So why a year ago, you know, we said we want to use the HICOM coordinate. Why? Well, there's a lot less mixing, a lot less spurious diapycnal mixing. You preserve dense waters. So we want our hybrid grid to be as isopycnal as possible, to have as little spurious mixing as possible. And the way the HICOM 1 coordinate works, it says I've got 2 levels, Z-star and isopycnal, and I pick the deeper one of them. And if you want to configure your grid in such a way that it picks the isopycnal one as much as possible, you make your Z-star levels really shallow. So these are the Z-star levels as a function of depth and index K across the x-axis. The green line is what we were using in our Z-star simulations, not the hybrid ones, just the Z-star. The yellowish line is again OM4, and the blue line is what we have been using in the hybrid coordinate here in CESM3. Super shallow. The 40th interface depth is only still at 100 meters. That's out of 70 6 interfaces, including the top. The 50th interface is only at 150 meters deep. It's very shallow. And that's because we want it to be as isopycnal as possible. Okay, so this is a section at the date line from World Ocean Atlas data in the southern Pacific, right? Only the southern hemisphere, Antarctica on the left, tropics on the right. And I'm only showing the first 46 interfaces, and I'm also not applying the maximum thickness. I'm only doing, Z-star level versus isopycnal, which one's deeper. And you can see near the Antarctic margins, it's basically just Z-star all the way. And that continues. And if you look back at what the grid does, it's very, very, very shallow, and then it has super fat layers at the bottom so that it can reach the bottom. It has to reach the bottom. And if you start really shallow, eventually it's going to get really thick layers, right? So near the Antarctic margins and in the Arctic, you start really shallow and you resolve the surface of the ocean really well, and then you have really, really fat layers. And it doesn't matter if you use DZ max. You might say, well, wait though, I said DZ max, the maximum thickness is 250 meters. When you get to that last layer, it has to reach the bottom. And if DZ max is 250, but it's a kilometer to get to the bottom, that bottom layer is going to be a kilometer deep. Okay? So you get fat layers even if you try to limit the thickness. Here in the tropics, this is a 50-meter thick layer within 50 meters of the surface. That's a problem. All right. And then over here at 50 south, you have a 250-meter thick layer that starts 100 meters from the surface, and that's a problem. Those ones you can fix with the maximum thickness. You could say, all right, this is like layer 15. I only want layer 15 to be maximum 15 meters thick. Fine. But this one's layer 42. And you could say, well, maybe I want that one to be like maximum 25 meters, maybe 50, I don't know. But guess what? Over here at high latitudes, layer 42 is close to the surface. But if you follow layer 42 further down, it gets to like 2-3 kilometers deep in other parts of the ocean. And over in that part of the ocean, it wants to be a few hundred meters thick. And if you're limiting it to 25 meters or something, you are making it not isopycnal. You're getting spurious mixing. So there's some art to this part of it. The other part was a little bit more mathematical and straightforward, but this part is a little bit hard. So what have I done? Well, it would be nice, let me briefly comment, it would be nice if the maximum layer thickness were not a function of which layer you're in, but rather what depth you're at. And that's something I would like to pursue, maybe again this summer when I have more time. Yeah, or somebody else might do it before me, I don't know. But I have to stick within what I've got. So what I've decided to do to deal with this is to change the Z-star levels. Not to try to fix this problem of having thick layers near the surface by tweaking the maximum thickness, but by just changing the Z-star levels. And I make them deeper, okay? Which means that the grid is not as isopycnal as it was, but the trade-off is that I avoid having these really fat layers near the surface. So this is, the red line is my new grid. I think it's easier to see in this plot. So I have some 10-meter resolution in the top 100 meters. That's what we had in POP, so hopefully that's okay. But it means that grid, it jumps down to 100 meters depth pretty quickly, much more quickly than the old grid. The old grid was doing 40 layers before it got to 100 meters deep. I'm doing 14 layers to get to 100 meters deep. And then it stays shallow. So then I go back to thin layers. I stay shallow to try and let it reach down and grab the isopycnal. And so I still, over here at high latitudes in the Southern Ocean, I still have a thick layer, but it's not as thick, and it doesn't start as close to the surface. So this layer over here is only 150 meters thick, and it starts 200 meters from the surface. Whereas in the old grid, it was 250 meters thick, and it started 100 meters from the surface. Okay, so there's always a trade-off, but I think this is an improvement, and it seems to help with the mixed layers. There's one other consideration, so I'm kind of going chronologically through how I actually have looked at this problem. So I got to here, and things were looking okay, except for the AMOC. Everything but the AMOC. The AMOC was too weak and too shallow. So the AMOC, the deep limb, you get dense water overflowing the Greenland-Scotland Ridge, the Denmark Straits, and the depths at which it overflows. So it overflows at maybe 600 meters, but then it goes down the shelf to 1,000 meters or so before it drops off. And if you have spurious mixing in that water, you get rid of your dense water classes and you get rid of the deep limb of the AMOC, and your AMOC is too shallow and too weak. So I want to have isopycnal behavior in the grid at those depths, but those are dense waters close to the surface, and I want it to be isopycnal, and that's antithetical to what I was just doing over here. So you have to sort of tune a little bit. So this is the kind of plot I was looking at, where I plot the sigma k target value versus the corresponding z star depth. So here's what we've currently been using. These are values that are densities close to the overflow density. So if you pick one that you think is relevant, 37.1, you look up here. If you have water at a density, a sigma 2 value of 37.1, if it is below about 500 meters, then it's isopycnal. If it's above about 500 meters, then it's not isopycnal. It's Z star. And so you kind of want this curve for whatever grid you're using to be towards the right, so that you're more likely to be isopycnal in this range of density values. This is what we're currently using. Works actually quite well. This is the OM4 value, and then this is my latest one. Not as good, but I tune this by, I said, like, I'm taking the 95th percentile, I tune that. I plot all the lines for 95th percentile, 96th percentile, 97th percentile, and I picked the one that looks like it's okay. And so with this configuration, our AMOC is not quite as strong as it was, but still pretty strong. I think hopefully strong enough and deep enough to be acceptable. I don't have time I didn't have time in this talk to show results, but Gustavo is going to show some results this afternoon. A lot of things get better, mixed layers in particular. AMOC does get a little bit worse, but not too much worse. I got a lot of input on this from people who are listed here, so thank you. But if there's anything wrong, don't blame them. I have, as we heard from Jean yesterday, I have applied this to develop grids for the last glacial maximum simulations, and I would like to use it for regional configurations like the Arctic or the Southern Ocean configuration, where if you use the current global configuration, you're leaving a lot on the table for those regional configurations. So that's it. Thank you.
Thank you, Ian. Questions from the room first? Bill?
Yeah, so for the last glacial maximum, you're using reconstructions of temperature and salinity, and
I actually,
is that what you use?
Initially I used an old POP simulation, and then it wasn't behaving as I expected, and I realized that the behavior in the MOM6 simulations was, the density classes were a little different from what was in my POP data. So then I took an existing POP data or an existing MOM simulation and directly used that to set this, and that was the most recent, the February 20th or something one that John showed yesterday.
Okay.
In terms of regional configurations, what are the steps that might, can you use a pathway to make this more automatic, skipping some of the art so we could put it into Crocodish or something like that?
Yeah, so I've already got all the World Ocean Atlas global data processed. And so all you need really is a mask for whatever region. And then instead of taking the 95th percentile globally, you take it over your mask for whatever region you're interested in. You probably at that point, it's dangerous to just use it. You should probably look at it first, right? But I think it's not a big effort to do that. For the Southern Ocean though, Sigma 2 is often unstratified. And so it would be better to use Sigma 0. Sigma 2 can be negatively stratified. So it'd be better to use Sigma 0 for that, which would just require a little bit of recomputing of stuff. Can you do that in HiCom1? Can you say, I want sigma 0 instead of sigma 2?
If you use sigma 0, you cannot represent Antarctic bottom water as being underneath North Atlantic deep water, which again, this is complicated, which is why it didn't get solved 40 years ago. It were simple.
So there's more work to be done for the Antarctic margins, unfortunately.
So you mentioned making the maximum thickness a function of depth, which you put in the logic. Cool.
Right.
How would you feel about making the target densities a function of space or time? I note that HiCom itself has made it a function of space because you have places like the Black Sea that are mostly disconnected at any kind of depth from the rest of the world, and the coordinates you use for the rest of the world are wildly inappropriate for the Black Sea.
Yeah.
For the last glacial maximum, if you're evolving the densities slowly enough, we might be able to put something in where it kind of automatically evolves itself towards something that is consistent both with the model is doing and your criteria of where you think you want the resolution to be.
Yeah, so time evolution is very straightforward. At least conceptually, it's not cheap to evaluate all this stuff, unfortunately, but you know, you can certainly do it. In terms of having it vary as a function of space, like just as a function of latitude, you can build that into my method easily. You do a zonal mean instead of a global, right? I think you would just want to make sure that the sigma 2 target values vary slowly, so that so that you're not generating a bunch of spurious mixing.
Slowly, or where they're buried in rock.
Right.
Right. So the Bosphorus is a lovely place to make that transition. And as far as the expense, it strikes me that the calculation you're doing to calculate this vertical coordinate is almost exactly the same calculation we're doing for the vertical structure of the internal waves. They're the same modal calculation, maybe with slightly different boundary conditions. And we're doing that every time step already.
I'm not actually using modes. One thing the reason it's expensive right now is because I take World Ocean Atlas and I interpolate it to a 5-meter grid first. And then I do all of this. And I do that because on the native World Ocean Atlas grid, you get a strong imprint of the native grid on the results. So I do an interpolation to high-res first. I have not explored trying to back that off to make it cheaper, and like where's the trade-off between how much resolution do you need to avoid getting the native grid effects. Yeah.
Any other questions for Ian online? If not, let's thank Ian one more time. We'll have a lunch break now, and we'll be back at 1 p.m.
All right, we got 3 talks in this last session, starting with Baylor, and then a discussion. Go ahead.
Great. So actually, there's a lot of discussion involved in this, I hope. So this is a not very exciting title. And it's, in some ways, not a very exciting topic, but I think there are some exciting points to make. And particularly we have open call for a couple of community review papers that I would love for people to join. I'll talk about that in a little bit. So I'm going to talk about the CMIP7 ocean data request process and some of the outcomes. For those of you who are not in this, the ocean data request, or really it's the ocean and sea ice data request in this case, is the request for the variables, frequencies, and maps for CMIP7. And I'll get more into details about that, but this comes from the CMIP IPO, International Program Office, out to all the modeling centers. It's gone out a couple times already in kind of draft version. There'll be another draft at the end of the month. So there has been a reorganization at WCRP. There are now different rings, and all of those rings are connected together by the ESMOS, the Earth System Modeling and Observation Scientific Steering Group. I'm one of the co-chairs of the Earth System Modeling Scientific Steering Group. And then that group is trying to coordinate better these out branches in different directions. So WGNE works on kind of numerics. WCSIP works on S2S, initialized forecasts. WigOrc is brand new, which is going to work on observational data sets for a variety of observational products that will be useful. And then the WGCM has CMIP and WIP underneath it, which are the bodies that organize and coordinate CMIP. CMIP is by far the most complicated of this during a CMIP cycle. So there's another international program office that's funded that has full-time staff working just for the CMIP IPO. And then there are 3 full-time staff members who work with ESMO and try and get the rest of the piece together. We try to work successfully together. These are the goals on this side for what ESMO sees itself as doing. So advancing predictions and projections, so both within the initialized forecast and kind of traditional climate modeling side. Improve monitoring, understanding, and attribution. So those are some of the top level questions about climate that span over this, whether it's an observational perspective or a modeling perspective, and also actually weather and climate. And then advancing and harnessing emerging technologies. So not only are you thinking about traditional climate models here, but we're also thinking about machine learning approaches, making data sets that are appropriate for training machine learning, all of those kind of things. A big branch within work within this emerging technologies subpanel. So, but now to jump on to CMIP 7. So CMIP 7 is pressed by a few upcoming events, the IPCC AR7 and the global stock take that comes shortly after that. The UN has decided the schedule of these, so this has very little to do with the WCRP planning process. And so when a new CMIP cycle needed to be delivered in time for AR7, the idea was that there will be a fast track of just the few most critical simulation types. And so the DEC, the 1% CO2 and quadruple CO2 kind of are part of that, but so are scenarios, and then also historical runs, as those are the most commonly used pieces for the assessment report. And then there are a few other weird ones, well, weird to my mind, but they're targeted at specific questions which now have ended up in the AR7 scoping. So OMIP, one that a lot of us have participated in, is not part of the CMIP 7 fast track. So OMIP is here in the community MIPS. And the concept is that the AR7, if they want to talk about OMIP, they can talk about the OMIP 2 results that are already published. And now we're actually doing a lot of regional analyses using OMIP 2 runs and low res and high res. So those data already exist. Those papers are already there for them to draw. And I'll talk about the next generation of OMIP in a second. And the other thing that is also interesting here is they're talking about having the new forcing data sets come out often rather than coming out in sequence with CMIP conversion cycles. That's sort of in discussion with a lot of different groups involving the observationists and the integrative assessment modelers and all those things to try and make that more of an operational product. So even in between CMIP cycles, you could run with historical data that comes up past when the CMIP 7 models were run, so that every year or so you could actually give an update where the historical is based on observations, not based on whatever. All of that is kind of coming along. Those are the process. Okay, so now the specific to us, the Ocean and Sea Ice data request. So the big questions are, which variables do we need? How much storage does that imply? And a big question is complexity versus compliance. So this is a request, not a mandate. Modeling centers deliver the variables they find it convenient to do at frequencies they find it convenient to use. I guess they might not be able to exceed the frequencies that are requested, but they certainly don't have to deliver all the variables that are requested. And there's something like 60% compliance, I think, was about right for CMIP 6. So about 40% of the variables were not uploaded by all the modeling centers that were participating. So, and part of that is because the variable lists get very complex and you might have to do code, or your particular model might not be able to deliver that. The storage complaint pieces might be there. And then, so the more complex it is, the less desirable it is in some sense. So you'd like to simplify, you'd like things to be very clearly defined, the variables, so that everybody can deliver something that is comparable across all the modeling centers. That's the goal. And so there's a big question every time you go around the cycle, the updates to nomenclature. And so there's the whole CF compliance group, which is developing nomenclatures. And then there are updates to definitions of variables, which are also important. So some of you participated in the Griffey's et al. 2016 paper that updated some of the definitions. I'll get to a paper that we're working on now to try and do something similar. International Buy-in, Modeling Center Buy-in, lessons learned was a big piece. So one of the parts that we tried to do in this conversation was how to take advantage of the things that went wrong last time and avoid those problems happening again, as opposed to a sort of theoretical idea of what we should be putting in, like closing a budget or something, to say like which variables do we actually need, which that weren't there, or which variables ended up being not very useful in the multi-model comparison because there were inconsistent definitions across the different modeling centers. And so this paper, this Ocean and Sea Ice data request process, the CMAP IPO has led the process of selecting authors, deciding on that which has geographical, gender representation, expertise, all of those things, and so people volunteered to join that, and then they did a selection process. So that was part of what the CMAP IPO did. So they took charge of that, which makes sure that any decisions made by this group are going to be sort of easy to slot into the IPCC without any trouble about those sort of things, or into other WCRP principles. But and then below, this is Providence, by the way, as seen from the water. That's a power station and I-95 bridge. There's a scheduled internal review of papers beginning March 7th. So we have about one more week before we have to have a complete draft of the first paper that'll get cycled around. There's a writing sprint a couple weeks later, and then the final freeze for the data request is at the end of March, and the final release is March 31st. So there will still be more opportunities for modeling centers to complain about that being inaccurate, inappropriate, jump in and critique the papers. There's a special issue of GMD plan, so all the papers will be in open review the way it normally is in GMD. And you can come in, and I think probably things will go to the screeching end in terms of like updates to model definitions and all that stuff. So I'm the lead on that, which I'll discuss later as well. And then Patricia De Hoffensieke is leading from the sea ice perspective. So we're the co-leads on that paper. There are about 15 authors total. Okay, so we did not, so as I said, the CMAP IPO organized this process for all of the data request papers. So all of them have a similar process where they have a kind of schedule and they're trying to sequence us together so that we're not getting, the Earth's energy folks are not getting way ahead of the ocean folks, because we need to talk together and compare. And so there are two. So they decided the way to think about this was as opportunities, and anyone on this team or outside could promote an opportunity, which just needs a kind of project description that goes along with it and some of the variables. It was our job to figure out the complete set of variables you needed to address the science underneath that opportunity. So the classic ones are ocean changes, drivers, and impacts, which is very similar to what the CMAP 6 critical variables were. The priority 1 variables from Griffey's is essentially equal to this with a few modifications. Similarly, there's the sea ice changes, drivers, and impacts, which is the sea ice variables that are also matched to that. These two have some commonality because you need things like upper ocean temperature in order to study sea ice, and sea ice in order to study albedo. And so there's a few refinements there, and hopefully we've done a good job on those. The other pieces of this story are more targeted, which kind of highlight some new things, and these involve the introduction of new variables into refinements or increased frequency. So the causality of polar amplification is one, which needs a lot of upper ocean information like mixed layer depth, ocean daily, sea surface temperature, sea surface salinity, that kind of thing. Plus additional a lot of sea ice variables that are after the polar amplification, plus atmospheric variables that are useful for that, cloudiness, reflectivity, all those pieces. Ocean extremes is something that we put in to try and promote that we'd like to have a few layers near the top. The surface and 200 meters is what traditionally has been looked at. Those two levels, so surface is really SSS, SSH, SST, all in dailies, and then also 200 meter dailies for those equivalent variables, well, not SSH, but and then also chlorophyll, oxygen, things like that that are traditionally put together with marine heat wave kind of concerns. So marine heat wave is a kind of classic thing you think in there, but there's also marine acid extreme events. These go out to the coarse resolution modeling center, but also the high-res MIP as a request. So we're hoping to get some of the high-res models in there as well. There are two on wind waves. One is really putting the output so that the CalClip project could go again and run offline waves to see how waves change under all of the climate models that are run. So they take sea surface conditions like currents and wind conditions at high frequencies, put them together, make waves from that. And then there is a new one for online waves. So CESM has online waves. The GFDL model has online waves. Others also have online waves. And so we're requesting a few of the key variables, both to figure out what the waves are doing, but also to figure out what the impacts might be, whether they're coupled to mixing and other things like that. A few of the indicators. This one is still kind of in development. Unfortunately, it's complicated. And then there's a paleoclimate one, which has similar changes in drivers, but long time scale on the simulations that go for a long way. And this is the setup for the PMIP comparison. PMIP being part of CMIP as opposed to an independent community MIP this time. And then there are other groups, like I mentioned, the Earth's Energy Budget Opportunity is an Earth system model data request, but it's so tightly linked because most of the energy ends up in the ocean that we talked a lot in the development to make sure that we're delivering the energy variables they need to do the energy budget of the whole system. All right. Are there any questions about this? Because I'm about to change gears substantially. Yeah, Keith.
In the previous iteration, the Ocean BGC was a separate manuscript than the Ocean Physics. I see you've got some Ocean BGC here. Is all of Ocean BGC melded? Is it all in one manuscript, or is it?
No, it's distributed between us and Carbon Cycle and a few other places. So it would be extremely helpful to have a lot of careful eyes coming from the Ocean BGC community to make sure that we have not lost things in the cracks. So Michio, last name, Omayishi, I think. So it was making contact between those groups, and he was working on the Carbon Cycle side, the Carbon Cycle Task Team side. And so he had a bunch of different hooks. And so he was supposed to make sure that we weren't missing pieces in between that story. But the ones that fall in between the cracks are the ones I'm most worried about. So any input to those would be greatly appreciated when these drafts come out. Yeah.
Are there any daily fields that are not two-dimensional?
There are a few that are a handful of layers, not 3D fields daily, I don't think, for anything.
Okay. And are there any integrated quantities that need to be incorporated into the underlying models before you can actually run them through the?
Yes. We're going to come to that in a minute.
Here. Okay.
Yes. For a very good reason with a very limited scope. And again, it's a request, not a mandate.
Okay.
But we would love to have it for a particular reason. Okay, so there are two other ocean and sea ice papers that I am involved in. And these two, I'm, together with Alistair, putting together a team of the interested or the volunteers. So if you would like to contribute to these, just I mean, one is called OMEP for CMIP 7, which is a very similar approach to how Griffey's OMEP for CMIP 6 was written. And it's not only this sort of listing of the variables, the listing of the variables would go in that previous paper. This one is more like, let's explain the science behind why we decided to redefine a few variables. I'll get to those in a second. And then there's a second one, which is there is a spin-out task team within CMIP, but I don't think that they are taking seriously the full spectrum of how oceans need to be spun up, not just for CMIP, but also for coupled weather forecasts, S2S, etc. So there's a spin-up paper that's kind of in the forming, which has been a conversation between people like Tim Graham on the coupled weather side from UK Met Office and Andy Moore from the S2S community and Andrea Mollad from NASA about what are people really doing? So CMIP OMEP for CMIP 7, these are kind of the headlines we have right now. So Anne-Marie Tregier looked in careful detail at the mixed layer depth from the OMEP runs and CMIP runs from CMIP6, and found that the mixed layer depth was inconsistently defined across the models. Even though it was a sigma-based delta sigma, some people use the surface, some people use the top grid cell, some people use 10 meters. So we need to use the same. Some people also use different thresholds, which was hard to figure out, but a couple of models used a different threshold that was more appropriate for Arctic. We was interested in Arctic. We used an Arctic threshold. It was hard to uncover that that was the case. She also shows that the biases that are introduced by those different definitions exceed the biases that we were trying to correct for in mixing, changing mixing parameterization. So we need to do it consistently. It doesn't matter which definition of mixed layer depth, we use, we definitely need to be consistent. So that's one fix. Most of the models last time around were not TS10. A handful are TS10 now. What do you do when you have both and you're trying to compare? So there was a paper put out by Trevor McDougall with one way of doing it. There's some discussion around this. Some of these integrated variable requests are supposed to be do your best job at what you think the appropriate heat content variable is and upload that. Sea level contributions. So there was a sort of revolution in the specificity of definitions from a paper that Jonathan Gregory led. And so there's some updates for specific requests, like what kind of geoid are you using, things like that, that are hopefully going to just tidy up some of the loose ends around the sea level. And then this paper also, I was encouraged to, but we have not yet settled on this, to consider doing the OMIP3 protocols as part of this paper, the same way that the OMIP2 and OMIP1 protocols were part of Griffey's et al. At first, I thought that was going to overload us, but I have promises from the OMIP team that that's not going to be a lot of overhead. I think that's going to be fine because we're basically just continuing the plan from OMIP1 and OMIP2 for the basic setup. Ocean FAF-MIP, so another MIP from last time, which is, I think is hilarious because it's called FAF-MIP because it's sort of faffing about with fluxes. But the faffing about with fluxes is trying to understand how uncertainties in fluxes impact the concentrations you find and so if the fluxes were wrong, obviously the ocean models will disagree in their concentration fields, but it doesn't have anything to do with the ocean models, it has to do with the fluxes. So let's get a little better at that. So there was a coupled version of that, which Jonathan Gregory led and had lots of interesting results. But in conversations with him, he thinks that they actually probably got the understanding out of it. But there was an uncoupled, just ocean and sea ice version that was Todd et al. Involving Larzana and others, which was sort of beautiful, and it revealed how the subsurface processes were reflected by changing surface pieces. So we're trying to find a streamlined, very light version of the Ocean FAF-MIP protocol to include as part of OMIP, because it's going to reveal a lot of intricate model details that are different among models in a way that we don't have access to right now. Here, the integrated variables, part of the request is to try and match what traditional observations are. So 0 to 300 meter heat content, 0 to 700 meter heat content, 0 to 2000 meter heat content. Those are, and same with salt content. Those variables are the way the observations have been doing it, and they're not going to change because we're not doing it. And there was a lot of uncertainty even last time because we didn't have exactly those vertical integrals set up that way. I expect it to be much greater this time because we're using hybrid coordinates and other things that make it very hard to figure out, even with thick cello, monthly thick cello, monthly temperature, we're not going to get back to what the heat content actually was doing. So just for those few variables that are so critical to diagnosing the water cycle and the energy cycle, just at a few levels in the vertical, we're requesting those to be integrated online in whatever vertical coordinate you're using so that we can turn those 2D maps into basin by basin or global Earth system pieces. And then there's a last category that we were going to address which is the fitness for global carbon and heat budgets. So the carbon folks, the global carbon project, before they consider a model as being ready for that, they have a threshold on the trend of global carbon during the pre-industrial. They're like, if the global carbon is not smaller than that, they just don't use that model for that comparison set. John Dunn suggested that it would be really nice to have something similar for the ocean heat content, that we have a threshold where we say, if it's not below this, the model's probably not doing a good enough job. This is closely related to the mean ocean temperature that's gotten shown a few times already as sort of a threshold. And hopefully that will help modelers kind of get their heads around what a reasonable limit is. Yeah, Bob.
Is this a rate of drift or a deviation during the historical run from?
This is not during historical, I don't think. We haven't formulated the answer. We just know that this is something that would be good to have in this paper.
Okay, but if we did it at a rate of drift, it says spin up your pre-industrial controls long enough and anybody should be able to get there theoretically.
That your drift is below this before you start your historical run. Spin up requirement without, too much specificity about exactly how you spin up. Yeah.
Okay, because that's something everybody should be able to get to. Getting within a tolerance means you're going to start excluding groups, and that's where you're touching a third rail on all this.
Exactly. So that's one of the reasons why this is not the CMEP approved paper. This is a community recommendation coming from outside. And then among these variables that we're talking about, some of them are priorities for the CMEP spin up and fast track. So there's that. Okay. Last paper to talk about ocean spin up. We're basically trying to organize a group, which will be an ESMO task team, to write a paper, which is a state of science review covering practices in ocean timescale theory. CMEP, standards for spin up, which have never really been documented because every group does something different. OMIP spin up, which we do have a protocol for. We can bring that forward. And then coupled NWP and S2S spin ups, so data assimilating spin ups. How do they do it? Do they run it for 500 years before they start assimilating? No, they do not. What do they do? What do they not trust about the models? And then in addition, there have been some recent innovations, which we're going to try and cover a little bit as well. The E3SM team is going big into using emulators to accelerate spin up. So they're going to train an emulator on their high-res models and then spin up the high-res models by initializing from an emulator. And so the emulator is, 100 times faster than the real model. And so that's their target. So they can spin up as long as they want under the emulator, but then there will be an adjustment shock. So we're going to try and get the state of what they're doing. Samar Kadiwala has proposed a new method for accelerators. He had it in mind to do it for BGC. But it could be used for other spin up purposes. So we want to make sure that we want to get that piece. And then, as I said, just to get some ideas of what's going on in the data assimilation world. This paper was really motivated by some of the groups I was mentioning before, such as EVE, saying that they're going to do kilometer scale coupled models and it's going to be the best forecast there is. And I essentially said, but the ocean is going to be drifting faster than anything else, and that's going to be the biggest signal in your energy budget. And they said, what do you mean? And I think we need to write a paper to explain how hard it is to do that right, and some of the approaches that work or don't work, and then maybe people will be able to innovate against that. And so hopefully the emulators and accelerators are reasonable examples of some of the kinds of thinking that are innovations. So, like I said, this paper and this paper, please contact me if you want to join. I think that's it. So, to discuss, the first question is very serious, is involved. Why am I doing this? You might ask that question yourself. Other things, is ESMO useful? Is CMIP too bureaucratic? Are there other variables we need to consider for the data request? Do you want to join the community papers? Please do. That's it.
I'm going to propose that we think about these and come back to them during the discussion because we're already over time. And I, for one, have to leave on a schedule today.
Great.
So I don't want to get too far behind. Sorry, we'll come back to it.
And slides and you go on.
Is there a physical plug-in or?
No, you have to join.
Sorry? I didn't see any random slides in there. Oh, what's this? Oh.
I know, I haven't figured out how to do that yet. I have to, it's a software development process.
Is there a protocol for
Right about this?
documentation? That's the model. Configure your.
No.
No.
It's wonderful if there is. There's some documentation of the data repository. So there's a documentation task team that is going to try and distill these papers into better docs.
We filled out spreadsheets of various model configuration details.
Yes, exactly. But those are kind of hidden. So it's supposed to be a documentation.
Like we fill it out.
They're supposed to be, they're there, but they're not easily interpreted. So there's supposed to be a documentation that sort of fleshes out why you
Okay.
want to know that. Links
Thank
to
you very
these
much.
papers, et cetera.
So today I'm going to talk a little bit about the work that's going on at NOAA GFDL, develop our counterpart of the next generation of CESM, specifically the OM5 ocean model configuration. And I'm going to touch on some related regional model development. I think one of the critical points here is this is the contribution of an extraordinary team of people. My contributions personally were relatively modest, and so bear that in mind that this is very much a group effort. GFDL's next generation of global models, we're going through a whole refresh cycle, and it ranges everything from a high resolution atmospheric only model for weather out to the two columns on the right, which are the ones that are most relevant today, both of which are using an updated version of the OM6 based OM4 model being updated to OM5. The ESM 4.5 is our answer to the fast track CMIP7 call. We're only entering with a full Earth system model, not a physical model. And this is one where most of the effort has gone into improving the atmospheric chemistry, the biogeochemistry, but we're also increasing the ocean resolution from a half degree to a quarter degree, but still at the same 75 layers, plus a number of contributions that on the ocean side that are already available. This is basically being frozen in a matter of a couple of months to meet the deadline. The second one is our CM5, and this is our physical climate model. There are two versions of this, one a lower resolution, quarter degree ocean, the other a higher resolution, 1/12 of a degree ocean. Both are coupled with a higher resolution atmosphere in some versions. The lower resolution ocean is going to be available with a target date of 2026, so it might make it for some of the CMIP7 stuff as a late entry. The higher resolution one is targeted at a date of about 2028, and it's reflecting the fact that it just takes longer to do everything with higher resolution model. Critically, one of the big changes that we're really thrilled about is we will have fully interactive dynamic ice sheets in this. And I'll have some animations there later. On the ocean side, one big change is that it is now fully non-Boussinesque, and these are both geared towards directly simulating sea level, including its regional variability, no after the fact corrections and whatever. Okay. At the same time, GFDL is actively working through this Climate Ecosystems Fisheries Initiative, which we will hopefully be renaming the Blue Economy Initiative. But this is basically a set of regional models covering all of the coasts of the United States with combined physical and biogeochemical models with offshore boundary conditions that are being generated from various models, from say a long-term climate model or from a data assimilative initialized seasonal decadal prediction model. And these include some of the configurations you've heard about earlier, but also the one that's kind of my favorite is this guy up here. We have Great Lakes, including Niagara Falls and a hydrostatic ocean model. It works. It's cool. Okay. Now, one of the big goals of the OM5 effort is to have this complete representation of the cryosphere. We have something that is working. There are a few limitations on the vertical coordinate and the way we're doing the time stepping, but everything else is working. And it is
animated here in these very early pictures showing the sea ice expanding and contracting. The icebergs, it's the little blue paths. Now these are point icebergs, but we are working on representing them as tabular icebergs, occupying space, breaking up, changing the albedo, getting stuck, doing iceberg stuff. And then what you'll see in the colors in the ice sheets, this is the ice sheet thickness change. So these are dynamic and thermodynamically active ice sheets, all synchronously coupled so that you can have a grounding line. If you add the tides, which we're planning to do, you can go up and down with the tidal cycle.
Ice
So-
shelves too.
What?
They're ice shelves too. They're just not shown.
Oh, they're there. There's an ice shelf right there. That's a Ross ice shelf. Ronnie Filchner. Ice shelves, ice shelf cavities. It is attempted to be a comprehensive treatment of the ocean and marine cryosphere, fully interactive on short time scales. We don't reset every year. They're running together in real time. Glaciologists think we're crazy when we describe the time step we're using for the ice sheets, but that's another story for later. So all of these capabilities that we are working on and are putting into the MOM6 ocean model are intended to fill gaps in the scientific capabilities of our previous CM4 model. We really liked our CM4 model. It was really good, but we are trying to address the fact that we could not directly simulate sea level rise with the interactive ice sheets non-Boost and S formulation. Explicit ties, including online gravitational self-attraction and loading, and improved representation of bathymetry. We are looking at some of the biases and limitations in the tropics and mid-latitudes by looking at how we're treating mixing in the boundary layer. And some of them you've heard about today or should have heard about yesterday, but we're increasingly moving towards energetically constrained mixing to address the fact that mixing in the ocean is not something that is static. It will evolve as we go forward in the 20th century. You cannot simply calibrate it so that it worked in the 20th century and expect to get the right answers. And so we're doing a number of things in that direction. We're also trying to address polar ocean and sea ice biases by drawing in improved sea ice physics. A lot of this is coming in via IcePack. GFDL uses IcePack for legal reasons. We don't contribute back. We're sorry about that. Fix the license. We'll happily contribute. But we're also looking at how we're doing the ice-ocean coupling because of the model as a whole runs, but there are some instabilities and oscillations that set in and that lead to mixing in places where it ought not to. And in particular, in the Arctic, we're looking at latitude-dependent internal gravity wave, internal tide specifically driven mixing that has improved one of the big biases that we had in our previous models. We're also looking at the deep ocean through a variety of things, including trying out better vertical coordinates, although as we heard earlier today, that's a tough one, and that one's kind of lagging a little bit behind, but also improvements to things like shear mixing and the bathymetry. And then, of course, the Great Lakes, because for U.S. climate, interactive Great Lakes really matter. Ask anybody in Buffalo during a lake effect snowfall event. And many of these are going to be in the main version of OM5. Some of these are going to be in kind of more experimental versions. We think we have the technical capabilities, for instance, to simulate the tides directly and accurately, but it opens up a whole can of worms that Baylor didn't even touch on when describing the data requirements if you have tidal cycles at 18 years down to 12 hours. So just because you can do it doesn't mean it's necessarily the best tool for now, but there will be applications of that going forward. Okay, so overall, we have a mission statement, and as everybody does, we have a ChatGPT generated image to illustrate it. But basically, we're pulling together in a concerted effort, which has involvement from something like 20 people, both GFDL feds but also kind of academic partners, some former postdocs, and so a large group of people, basically trying to treat the entire marine, ocean, and cryosphere system in a systematic way to address these biases. And as I mentioned earlier, all of the changes are directed towards one of these four big goals. All of this is open development, as you know. Everything is going into MOM6 in real time. All of these capabilities are freely available, and if anybody would like them, they're accessible. Also, from the standpoint of NOAA, it's worth pointing out that OM4 is the basis of the National Weather Service's Unified Forecast System GFS version 17. Everything we're doing in OM5 will be a natural candidate for a successor version when they go through their update cycle in a couple of years. So this is cutting across a wide variety of different timescales. Although I framed everything here in the climate context, everything we're doing is also applicable for everything from short-term ocean forecasting to season forecasting, decadal forecasting, which, you know, I think that for this audience, making that point maybe is a little bit obvious, but it's a point that we like to make because this is multi-purpose science that applies to many different purposes. So all of these are being deployed in OM5. This is kind of one example, and I think I spoke at this group or a related group before, but demonstrating that at a global scale, the non-Boussinesq formulation, when driven by the GRA Dodo forcing, can be reproduced with the Boussinesq version. The non-Boussinesq version, we don't do any corrections after the fact, and the regional patterns make sense. But we're going through a whole series of these changes that we've discussed. In the interest of time, I'm going to move along, though. Energetic-based boundary layer parameterizations are a big emphasis, and this is on the right is one of our big wins. This is from a paper by Brandon Reichel, where looking at the deep cycle equatorial turbulence in close comparison with large eddy simulations and observations, we found that with some modest adjustments to the background viscosity and to there's a cap on the energetic efficiency of the wind mixing in the boundary layer, we were able to go from the middle figure, which was what we were getting for the deep cycle in OM4, to the bottom cycle in OM5, and that is much closer, more closely aligned with the observations on the top. We've already heard, for instance, about the new sub-mesoscale parameterization from Bodner. Bodner's in, love it, it works really well. We're looking at improved wave-driven fluxes. Baylor mentioned that we have versions with a version of a wave model that Brandon Reichel has been working on. Again, waves will evolve with the system as a whole. We're taking into account. We have some machine learning, especially of the boundary layer parameters and some of the shape functions, which were kind of constrained by physical principles, but where there was uncertainty and the machine learning works well. And then we also have metrics of the boundary layer depth based on energetics. They are much more robust than any of these thresholds. We would love it if people would be interested in adopting them when they think they would clean up a whole lot of problems, but maybe that won't quite happen. Baylor, it's up to you to sell that one. Okay. We're also looking at physically consistent interior ocean mixing processes and trying to make them more realistic. So this is one example on the top. We had a background mixing parameterization that was based on curve fits from the Pacific, dating back to the 1980s. However, much of the mixing is driven by internal tides, and once you reach the critical latitude for the M2 internal tide, things aren't propagating. They don't propagate into the Arctic. So by using a much weaker background in the Arctic, we were able to go from the OM4 line, which has a lot of diffusion of salinity in the Arctic, to the OM5 line, where backing off of the mixing, we recovered something that looks a lot more like the real ocean. Similarly, on the bottom, we're looking at the propagation of internal tides actually using ray tracing. We can't resolve the internal waves associated with the internal tides, but we can capture their energy. We know how that energy propagates and where it breaks. And so we go from the mixing pattern on the top related to OM4 to the OM5 pattern, where a lot more of the breaking of the waves is more tightly tied to the topography. Yeah. You have more mixing in the Western Pacific than the Eastern Pacific. There's a whole lot of things that work there. That's been tried in an experimental version of the coupled model, and we like what it's doing. Okay. And then we've heard an awful lot about eddy mixing parameterizations. We're a part of the groups that are doing this, and there are some good things happening there. But overall, we are very pleased with some of the preliminary results from early prototypes of the full CM5, and that includes kind of broad metrics like sea surface temperature biases, where we took a model that we were pretty happy with, and it's even better. But perhaps even more importantly, if you look on the right, this is the pattern of wintertime sea surface temperatures associated with ENSO warm events. The observed pattern is on the top. What we were able to do with CM4 is in the middle. The one on the bottom is what we're getting with the prototype. And the pattern is more realistic, including significant warming in the coastal area. And this is due to both ocean changes and atmospheric changes. This is a team effort, both oceanographers and atmospheric scientists. Some of the key people involved in this are now looking for jobs. Let's just leave it there. But there are still some things where we think we can do better. So for instance, we are looking at an unexpectedly large sensitivity to one of the time steps used in MOM6. And we're looking into that, and we're hoping to be able to correct that. So as many of you know, MOM6 uses a whole set of different time stepping schemes, time steps to reflect the different dynamics, ranging from the fastest barotropic dynamics to the slower dynamics associated with the thermodynamics and the vertical remapping. The thermodynamics is using a much longer time step than the dynamics, and this is critical, especially as you go to Earth system models, which have lots and lots of tracers, because the cost per tracer is determined by this longer thermodynamic time step, not the dynamic time step, which is determined by Doppler shifted gravity wave CFL limitations. And we think that as we go to yet higher resolutions, we are probably going to be able to hold that thermodynamic time step at something like an hour or two, even as the dynamic time step has to go to a few minutes. And this is critical for making very complicated Earth system models work. Unfortunately, when we tried this out first in regional models and then in our full OM5, we found that there was an unexpectedly large sensitivity to the thermodynamic time step, where at least initially, if you had a shorter time step, you have more heat uptake. It's as though you're doing more mixing. On longer time step, there's still a sensitivity. These are runs that had a separate problem with mixing, in particular in the Mediterranean outflow being masked in an unfortunate way. But so there's a little bit of a nuance to the story there. But the bottom line is we would like to be able to do climate runs or seasonal runs or Earth system runs while taking a long time step without having an undue impact on the results. And after spending a little bit of time tracking it down, what Brandon Reichel found is he took two different runs, able to see this in only about a month. And so he did one with a 2-hour thermodynamic time step and the other with a 30-minute thermodynamic time step. The image on the top shows the difference in the vertically integrated diffusive work that is going on with the full set of parameterizations. The one on the bottom is when we turn off our shear-driven mixing parameterization, and the difference, the column on the right, the one with all the colors, there's a strong sensitivity to time step. The one on the bottom, there's very weak sensitivity to time step. So we think we've narrowed it down to being the Jackson et al. Stratified shear mixing parameterization. There are lots of nonlinearities. However, we think we have an idea of what's going on. So first, we simply can't afford to take a short time step. It would converge, but it is acting like a first order accurate scheme. We don't like that. But we think that the answer is that by adding forcing into the 6 equations that we implicitly solve for the entire water column for the shear mixing, we can do a whole lot better. And just a few seconds on the details here. This is the Jackson et al. Stratified shear mixing parameterization. It came out of a very successful GFDL, NCAR, and Friends climate process team about 15 years ago. And the idea here is that you implicitly solve for the diffusivity and a turbulent kinetic energy along with their impacts on the stratification and the shear. And this works really well in some three-dimensional quasi-steady state direct numerical simulations. But what we're finding is that in cases where you're perhaps taking a much longer time step or where there's temporal variability, that there's a problem. And it comes to the equations that we're solving. So we're solving something like 5 or 6 equations implicitly through the entire water column, doing it iteratively. But the equations that we're solving, the first two are the Jackson et al. Equations, but we're also taking a one time step update of the velocities and the density profiles so that it becomes self-regulating. It gravitates towards a Richardson number of about 1/4. But in the velocity equations that we're stepping forward for a time step, we're basically missing all the forcing terms. We left them out I left them out for simplicity. And so what happens is you start off with a certain amount of kinetic energy, and then it decays away in the solver. You don't actually use that state. You go back and use the diffusivity, march everything forward, so the model is all self-consistent. But the diffusivity that you're diagnosing is missing those shears. The other possibility, and this is one that I'm a little bit less, a little more concerned about, is the assumption that the turbulence is in equilibrium might also be a problem. Usually the turbulence evolves on a time scale of a couple of minutes. It's really fast. If you look at like Gotham runs, you will see they're taking very short time steps to capture the evolution of the turbulence. The target here is for climate models with time scales of an hour or two, but that's the other possibility we're going to have to explore. And so there's going to be a whole lot of refactoring and formulating. It worked pretty well for the last 15 years, but we're finding its limitations. And this is just kind of an illustration of how going back and focusing on the physical processes matters. This is one of the successes from Brandon Reichel, in which he showed that by decreasing the background vertical viscosity, we're able to keep that viscosity from suppressing the shears, and we're able to bring things much closer to the critical Richardson number. The vertical line here is a critical Richardson number of 1/4, the horizontal axis, the PDF, and then these are transects going across the Pacific. On the top is OM4, the bottom is OM5. And this has led to a significant improvement in the equatorial dynamics, which led to the improvement in ENSO, among other things. And similarly, in regional configurations, we're finding that the details of the shear mixing parameterization matter quite a bit. We have a lot of trawl data from PMEL, and for the purposes of understanding what your walleye pollock harvest is going to look like this year and next, you really want to know what fraction of the area on the Bering Shelf is covered by cold water. And so they have these trawl data going back for decades. With the original shear mixing parameterizations, we were mixing away too much of that. It turned out that was coming from the tides. There's very strong barotropic tides on the shelf. Tides have shears, but those shears don't last very long. And they're at large scales, so maybe this is the case where the time scales matter. But by adjusting one of the length scales in that 2-equation closure, you're able to get the figure on the bottom, and the correlations and the temporal variability of this cold pool metric on the bottom and the top. This is looking fantastic. So the fisheries folks are really happy with this. Some of us who are physics oriented are a little bit unhappy with the idea of tuning something we didn't think was quite tunable, but it says going back and looking at the physical processes again is worth it. Okay, so I just want to leave you with this. I know that times are a little bit uncertain, but I think this represents our continued role at GFDL in systematically advancing the state of ocean and cryosphere modeling across a wide range of timescales and for a wide range of purposes that map directly onto NOAA's mission and the needs of the nation. We've done a lot of our work at 1/4 degree resolution. There's been a lot of discussion in the last couple of days about 1/4 degree and higher, or 2/3 and higher. We think that a lot of the work at 1/4 degree maps very well onto our ability to run at higher resolutions and do very well. We have an 1/8 of a degree model that I haven't shown much of based on OM4. We were really pleased at how well they carried over. I think that the experience at NCAR with the 2/3, or with CESM, between the 2/3 and the 10th or 12th of a degree is analogous. We're doing a good job of spanning resolutions with our understanding of what's happening in the system and the two work together. Everything we've done here is publicly available via the MOM6 GitHub site, and I and the rest of the GFDL Ocean and Cryosphere modeling team are looking forward to hopefully working together with you for many years to come and continuing what I see as very fruitful collaborations with the CESM working group and all of our MOM6 community partners. I am more proud of the community that we have built together than I am of these extraordinary models. And I personally am happy to do anything I can to see that go on. well into the future. Thank you. How much time do I have for my backup slides, Gustavo?
How many you have, 80?
I think for the same reason, I saw Moma's hand go up. I think we're gonna probably hold discussion till the discussion at the end. So thank you, and just go ahead, Gustavo.
You can share.
Oh, I suppose.
Okay, so I'll give you an update on the status of the ocean component in CSM3. Last night, when we were at the Sound of Sun, Bob, I was about to, Bob was like, I have 100 slides. I was like, sure, I have only 15. So I added a few more. But, no. And this is a work that coalition, many people in the room and also as well. So we meet every Friday now or Thursday. I'm listening at all the participants and there's people that are contributing. Towards the end, I will show some fully coupled simulations where the entire CSM3 dev team is part of it. So too many people to list here, but please keep that in mind. This is the status of our CSM workhorse configuration, and in the middle, I'm putting what we had with POP just for reference, and then MOM6 is on the right. And then in blue, those are the new defaults as of the last time we presented about a year or so ago. So we, as it was mentioned before, we adopted the HICOM1 as the vertical coordinate. We also now made the flux profile mixing and Stokes similarity package default. We added Lithy, so this is a slightly modified version of the regular lead that Ian implemented. And we also now are using Oman as the solo penetration instead of Nixa. Okay, so those are the new defaults. Now in red, those are TBD. We haven't made a decision on this. So one is Bodnar et al., and the other one is backscatter. And then last in yellow is the estuary box model, which would like very much to have it, but unfortunately it won't be ready for CSM3. Although we did get a grant to work on this that we are very happy about. And then now I'm highlighting in green, those will be the focus of this presentation. So we'll talk a little bit about HICOM1 and then what Ian presented, like Ian's way of providing the interfaces versus what we did manually over the years. I'll talk about the Bodnar et al. And what we have been doing to tune that, and then also about a little bit about backscatter. And then finish with some CSM3 fully coupled. Okay, so Abby did a great job of explaining this earlier, so I'm going to go much quicker. And we just for like, this is the FFH, we have the F and the H here. And when you use that formulation for the slew function, you need to provide a length scale, and we use 1 kilometer in CSM6. And then in Bodnar 2023, they modified 1 to include convergence arrest by boundary turbulence, and then you have this LF that Abby explained earlier. So this is a dynamic way of prescribing the frontal length scale, and then you can reformulate your slew function and get rid of L. So then you also simplify that mixing time scale in the denominator of 1 that was kind of a not desirable outcome. So number 3 is what you have when you switch to Bodnar. And there's that CR coefficient that we talked about earlier. That's the one that you have to select. So a few comments. The original description in the paper mentions that there's a mixed layer depth, there's a boundary layer depth, so those are the little and big H. And the way it was implemented in MOM6, the big H mixed layer depth was computed via filtering of the little h, the boundary layer. So this is, I believe, also made that implementation. As of a few months ago or so, Alper implemented also an option to pass directly a mixed layer depth using a density criteria. So that is an addition to what was already in MOM6, and this is now under review at the main MOM6 repository. Okay, so when we turn on FFH with a length scale of 1 kilometer, on the left, this is the induced overturning circulation by the mixed layer eddies in sphere groups, and then on the right is the residual, where we're now summing all the terms, including mesoscale, so NLE, mesoscale, and Eulerian. So that's what we get on the right. That's the residual, and it looks good. Like things are going in the right direction, so we're happy with this. Thumbs up. And then when we tried Bodmer for the first time, we used a CR of 0.03. And again, on the left, this is the circulation by MLE. And now you can see it's kind of saturated, the color bar, so it's very, very strong. And if you look on the right, it reversed the near surface cell of the residual. And when I showed this to Gökhan, he was like, no, we can't. So thumbs down. We couldn't do CR 0.03. Okay, and then we tried reducing by an order of magnitude. And again, MLE induced looks okay, magnitudes are fine, but there is no restratification at the equator, or low latitudes, I should say. Okay, but if you look at the residual now, it's back to being acceptable. So there's pros and cons of that. Like it looks okay at high latitudes, but now there is no restratification at low latitudes. Okay, and in terms of so that's one way of that was our first approach for 2D Bodmer. The second one was looking at mixed layer depths. So again, top is FFH with 1 kilometer, and we're looking at summer mean mixed layer depth, and bottom is with Bodmer of 0.003. And if you look at the right panel, so this is the zonal mean, we see a deterioration. So the fact that we have less recertification at low latitude makes the boundary depths go deeper. And that was a thumbs down. No, so we, in addition of looking at the recirculation done by MLE, we also looked at the mixed layer depths, and with these two constraints, we start like tuning the CR coefficient. So then going back to that equation from Abby Bodmer, number 4. So now we said, okay, what if we make CR a function of latitude instead of a constant? So that's what we're doing now. And we tried all these profiles, there's 8 of them. V0 has a different shape. Now V1 to V8, we are using this function at the bottom, or we can play with the critical latitudes and the mean and the max. And I'm highlighting V8, the one in blue, the dark blue. That's the one we like, and we're pretty happy with it. So I will be showing results with this CR profile. It's not that symmetric from the equator, so we don't need to, if we're using Taylor simulations, we can use the same and no need to be tuning too much. Okay, so now back to FFH with 1 kilometer, and this is March mixed layer depth. This is the bias before, so this is model minus the de Boyer. And now bottom is the Bodmer with the CR as a function of latitude version V8. And we'll do the zonal means here. And we see a lot of improvements. And my cursor to show. Oh, that's too bad. So if you pay attention around 50 north in the zonal means, blue is 82, which is the one with FFH, and then orange is 42, which is Bodmer with VA, and then in gray, that's the OBS de Boyer. So we're much closer to the OBS, so we got rid of that big spike. Similar at mid-latitude, so around the western boundary currents in the northern hemisphere, we were able to reduce that mixed layer depth by significantly by having that big wider taper in CR. And if you look at the southern hemisphere, so Southern Ocean, it may be slightly worse for March, but I mean, we cannot, we can take that in favor of the other improvements that we see in the northern hemisphere. Okay, so this was March, thumbs up. Now September, again, top is FFH, bottom is Bodmer. and this is the zonal mean. And now with FFH, we had too much mixing in the Southern Ocean for September, and we were able to reduce that somehow with this new implementation via Bollner. So it's a thumbs up as well. So as I said, we're pretty happy with this version 8 of the profile for CR. Now this came for free, so we were looking at the string function and the mixed layer depths, but then we ran the simulations for one cycle. And so we're now looking at the buoyancy contribution to potential vorticity. And so this is an indication of Antarctic intermediate water formation as well as mold water. And this is the Eastern Pacific Ocean. So this is from OBS. And then this is the FFH case with 1 kilometer. So, you know, it's not horrible, but it's kind of closing up that high PV value. And this is with the Bollner V8, which is pretty good. It's not as deep as OBS, but like it looks way more realistic to me. So a significant improvement, thumbs up. All right, so that was the Bollner part. I'm going to switch gear now and talk a little bit about the HYCOM-1 configurations. So Ian showed this morning the ones we are using out of the box, which I'm calling old, and the one that he came up with, the last one, which I'm calling new. And these are the profiles, and there's a lot of art that goes in here in addition to some of the math that you presented. In the following slides, I will refer case 42 has the old grid, and case 43 has the new grid. So keep that in mind. So the way that we look at this when we configure the HYCOM-1, we find it very useful to look at the vertical resolution across particular sections. So we have a bunch here. I'm highlighting these two in red, which is the ones I will show you today. So across the Pacific, and then across the subpolar gyre in the North Atlantic. So let's start with the Pacific one, and this is 42, so old grid. So I'm about to show you an animation where the thick red line at the top is the mixed layer depth. The color shows the layer thicknesses in meters. And then if you look closely, there's like thin black line in the background. Those are the interfaces. The distance between two interfaces should be the color, the thickness. And then the dashed lines are the sigma 2 targets that we provide in the HYCOM-1 coordinate. So if you see them parallel, if you see the interfaces and the dashed lines parallel, is an indication that the model is isobaric. And when they are not parallel, is an indication that it's Z star. So let me animate that. And by the way, the red dashed lines are the last 10 density interface, are the densest 10 densest interface that you provide, just to show you where they appear. Okay, so it's only 20 years, but like we can get a sense. We see the mixed layer going up and down. In the Southern Ocean, things look ugly, like at depth, like there's this staircase-like pattern. But then, like once you get close to 60 south, you can see the indication of your isopeak. As was mentioned before, if you look all the way on the Arctic, so on the right-hand side, it's pure Z star. It doesn't change in time. So we were happy with this grid, but the issue is, as Ian mentioned, there was a lot of manual tuning. So when Jean was like, I want to do payload simulations, what can you regrid it? Can you create a new set of targets for us? It takes a long time to retune it again, man. So that's why Ian made the new approach. So let's see how it looks like with Ian's grid. Okay. So now the color is a little desaturated, but you get a sense that it's thick because it's yellow. But the Southern Ocean, especially the first 1,000 meters, really close to Antarctica, is Z star. We don't see those staircases anymore. And then the way Ian designed, near the bottom, you see all this purple, so it becomes Z star, and like you increase the resolution again. Again, in the Arctic, we are Z star, but no, it was there's some similarities, some differences. There's no thick layers, which is important for BGC. Every time I show this to Keith, and we see like within the mixer that having very thick layers is like this is an issue for BGC. We have to fix. So no, we are happy with this grid as well. So we're trying to understand now what are the difference between the two, 42 and 43. Okay, I'm going to show you another one now. So this is for the subpolar North Atlantic. It's way uglier. So now this is going from on the right here is like just north of the UK, and then on the left is within the Labrador Sea. So this is a really way more complicated region to represent. This is old grid 42. It's like, I don't even know what coordinate it is at that. Now we see star at the top, and then at that it's just like being limited all the time, and it doesn't make too much sense to me. Now with Ian's grid, your Z star way deeper in the water column, but then up below that it's kind of similar to what we see with 42 or the old grid. Okay, so now we have a sense of the good, the ugly, bad, like let's see how the results look like. So 42 versus 43, summer depth bias. Okay, and here's the zonal mean. And 43 is better. Like is particular, we had this in the Southern Ocean. We were not able to reduce the mixed layer bias with Bodner or with KPP, and the grid like got us slightly closer to the blue block. So it was a positive overall improvement in the mixed layer, but the summer mixed layer that biases. And now is the winter. And again, we were too much convection in the northern hemisphere. We got slightly less convection, and this is with all the reasons and also this has Bodner, has FPMix, KPP, and with 43, by changing the grid, we reduced a little bit in the northern hemisphere, the mixed layer biases for winter, and then in the southern hemisphere, similarly, you had too much convection in the deep mixing zone. You can see the red patch on the map at the top, and that was reduced with the grid. So again, overall improvement, so thumbs up. AMOC looks reasonable in both cases. This is the time mean, and here is the profile at 26 north. The 43 is slightly different at depth. I'm suspecting perhaps because of the higher resolution, and Frank had some plots where he shows that perhaps we're resolving better the bottom cells, and now we have more ABW coming to northward. It's hard to see on the color here, but on the profile you can see that the orange one is slightly stronger at that. So again, overall, similar AMOC in both cases, but it's slightly stronger in the abyss with the new grid. Now, Dinamarca Strait overflow. So one of the last interaction that we had with Ian, he came up with a grid. We ran a case, and the AMOC was very different than the one we had out of the box. So we went up and looked at the Dinamarca Strait overflow and saw that with the new grid, we were not capturing well. So Ian did a new set of tunings. They came up with new interfaces, and that's what we were using in 43. But since then, we've been looking at the Dinamarca Strait overflow, and it's quite revealing. So big thanks to Fred for giving me this tool where I give it this profile on the left. I can then I don't have to follow the longitude or latitude. I can give you a section right across the Dinamarca Strait overflow, which is shown on the right. So you can see the seal depth when it gets shallow, and this is sigma 2 density. And you see already a signal of the overflow in this, and I will animate. So this is for over a whole GRA cycle. So you can see the source water, you can see the overflows going all the way to 2,500 meters. So this is with the old case. Now I'll do the same thing with the new case. And if you look at the right side, the yellows, there's a hint, this is like different than the one on the top. So let's look closer at the overflows. So now I'm taking a profile right at the seal depth, and I'm showing a half-molar of that profile as a function of time in 42, and I'm increasing the grid as well. So you can see high resolution in the surface, so this is Z star, and then you can see the lines kind of undulating. That's a signal indication that we became isopycnal, and then in red, this is the overflow, so this is the kind of the thickness of the plume, and it becomes Z star again as you go inside, because there's little certification in the region. So this is with the old grid. Now the same exercise with the new grid. So now it's Z star all the way. One thing to notice, like the interface between the plume and the ambient water is more diffuse in this case. On the one at the top, like you see more lines right at the interface. So we're resolving better than right at the edge of the plume. And it's hard to see on your screen, but it's less dense at the end of the one cycle with 43 than with 42. So the plume is thicker in 42. If you take a look carefully and see that you go like almost 300 meters. In 43, you're kind of like doing 300 and 400 meters. And then, as I said, you have higher resolution at the plume interface in 42, which is also should be more isopycnal there. So this is at the seal depth before the overflow goes down. Now it's the same thing, but at around 1,400 meters. So the plume has gone down like by almost 1,000 meters. So again, top is 42. We see Z star, like high resolution of the surface, and then you become isopycnal. And then you see a thick black line between the overflow and the ambient water. So these are multiple isopycnal interfaces there. So there is like you're kind of protecting the overflow below, and there's less mixing occurring because of that. So there's less entrainment in this case. That's my interpretation. Now the same exercise with 43. So right away you see the color has changed significantly. So the overflow is less dense in 43. If you look closely, it's also thicker. So there was more entrainment and it was sending. And there's less indication that of that high resolution at the interface. So 43, slightly thicker, denser plume is 42, higher resolution at the plume interface in 42, more entrainment in 43. I mean, I'm switching the order just to make you think more carefully. Okay, so that was it about the grid. Now switching gears again, energy backscatter. So Frank once said, I think he was the founder of the lab, there's no mistake in modeling, right? That was this was a mistake. Ian will remember, it was a weekend. There was like, the undercurrent is too strong. We need to slow it down. And then I talked to Ian, and Ian emailed and said, oh, I have this, the leaky scheme, and the way you can turn it into, not a backscatter is by turning off the backscatter. So he gave me the recipe, but it was on the weekend and I was sloppy, and I created a case and I added with backscatter by mistake. And I look at the run and it was bad, but Frank was looking more carefully, and that's how the whole thing came in. So anyway, a little bit on the backscatter. So this is a standard, the way we do the dissipation via biharmonic operator, and then we re-inject energy back via a negative Laplacian operator. And there's some details here, so we do some averaging. So Ian has the whole recipe in his paper, and it's slightly modification. We can talk more about it in the discussion if needed. One thing is the backscatter is only applied where the computed lead viscosity exceeds the background biharmonic viscosity. So in this model, only happens in the equatorial region. And these are the parameters. So you set usually equals to true, and then you need to provide a biharmonic constant. You're using 75. And then the lead fee CK is by default set to 1. That was my mistake. I should have, you have to manually turn it to 0 if you don't want backscatter. But anyway, there's no mistake in modeling. So we ran this case, and then what happens is when you turn on this backscatter, so this is now looking at equatorial undercurrent at 156 east. Top left is OBS, top right is POP, bottom left is without backscatter, bottom right is with backscatter, and here's the same for 165. And if you pay attention, there's these so-called Tsuchiya jets, which there's a hint of them in the OBS. You can see these jets coming off the equatorial undercurrent and down, and we saw them. And I will be frank, I look at that, I was like, this is wrong. And I'm glad Frank was paying attention. And Frank and Bill, they got so excited when they saw this that, it was like, wow, we've never seen this before in a low resolution model. So this was pretty cool. Another plot from Frank. So now we are looking at, we are 180 and plus minus 20 degrees in latitude. And this is a time mean, I believe. And the top is without backscatter, and bottom 44 is with backscatter. And again, you can see the Tsuchiya jets, but also there's this whole zoo of other jets that appear. And then on the right, this is from observations, I believe, a bunch of Argo and other stuff. And they find they see similar patterns, and the ones labeled A are the Tsuchiya jets as well. And it goes deeper, it's the same depth. So anyway, very similarity between the two cases. But as with anything else, there's nothing is concrete. When you run with backscatter, the Miron overturn circulation looks different, I would say. So 43, the top is on the left is in the Z space, the global MOC on the right is in density space. And then at the bottom is 44. So if you look at the equator, there's some different stuff going on. And when I saw this, I was like, maybe I don't know. It's wrong. I'm not used to see this, but there is some explanation. Maybe things are tilted, and when you do a zonal integration, that's how it shows up on the Miron overturning. It's less so in the density space, but you can still see some kink-ish around the equator. Anyway, this is all brand new, and we're still trying to understand what's going on. But one thing is, those jets are super important for BGC, so it would be super nice to have a BGC with the backscatter turn on. All right, so finally, put a couple simulations. I'm only going to show two cases that are relatively new. 127 is when using the new setting. So everything I talked about, Ian's new grid, Bodmer, and no backscatter so far. So Bodmer and Ian's new grid are including in 27. 25 was our previous baseline. So mean SST bias are similar. It's slightly different if you look in the Pacific sector, in Southern Ocean, it became red on 127, which is on the right. But overall, it's similar. In 125, we had this, if you look north-south, this bias. It was too warm in the northern hemisphere and then too cold in the southern hemisphere. And the atmospheric scientists were contemplating that could have helped with some influence on the Amazon region. That got slightly better with 127. And I think the Amazon bias also got slightly better with 127. But those are short runs, so keep that in mind. This is the mixed layer depth, zonal mean, biases and zonal mean. And again, by using the new grid with all the Wilson Zebels, we're slightly better on these biases in both hemispheres. And the same for September. So September, the deep mixing band was just too much. And it's a significant improvement now with new grid and Bodmer. There's something going on 5 north. It's very hard to see here because it's a small kink. But like every time now that we have, and I think that might be something when we add Bodmer. So we need to understand that. Profiles for the AMOC, again, like looking really good. 127, in addition to everything I mentioned, was also topography change. So that's why we're now getting a deeper AMOC, and the time series are looking pretty strong. So we're pretty happy with these simulations overall. One issue is the ENSO autocorrelation problem. So left is off, so it should take about 11 years to switch from
Months.
El Nino. Thank you, 11 months. They need to take 11 months to switch from El Nino to La Nina. And whereas the last two cases is like more 20-ish months. So it's just taking too long. And we'll fix with 127. But the variance is looking okay, although low. So this is a bunch of simulations we've done in addition to CSM1, CSM2, and OBS. And so this is the range, and the last two simulations I'm pointing here with the arrow, they are on the low side, so it's okay, but on the low side. And then finally, this is annual mean precipitation standard deviation. 127 is on the top, so we still have this dry patch in the eastern equatorial Pacific. It kind of went away in some of the early runs that I showed below, like where it got diminished, like 116 is looking reasonable. But then I kind of now seems like it's coming back. Again, these were short integrations. I don't know if it matters if you run the model for longer, these are much better. But no, that's kind of where we are. And with that, I will stop and take your questions.
Well, we're well into the discussion period already, so I think in order to make the most use of the time that we have, let's just open it up to discussing all the talks. Any questions for anyone or discussion? I hadn't seen some of those results about the overflow yet. So can anyone explain why the AMOC is still good, but the entrainment and the overflow is high? I thought those things went together. So the entrainment's bad, but the AMOC is still good.
Oh, yeah. Excuse me, it's different. We don't really know what it is.
Okay.
I mean, I just let's remember that. We sort of have an idea what the AMOC should look like a bit from Rapid, but actually what in training is going on, it's all below any observations and in fact, even the Rapid doesn't, you could argue it won't even see things that are not geostrophic because they measure the transport without measuring the velocity, you know, very many anyway. They have a few moorings, but a lot of it's done with a model in a way, especially near the coasts. So yeah, I don't know whether we really know what the entrainment should be. Do we? We sort of know, but
There was one campaign, but they were out there for like 3 months. So we have 3 months.
yeah, exactly. Yeah. So anyway, it's certainly different, and in a way I don't quite understand.
Not
That's the
necessarily
way.
worse.
I don't understand the difference, but I don't know what's right and wrong.
Chip on me.
But Bill, we do know what temperature and salinity are there.
Because it's
Yeah.
closer, so maybe we see more difference.
Yeah,
These are big enough differences I would expect to see.
But I didn't see what.
I would
the
expect
odds
if we showed.
Yeah, it would be
Yeah,
helpful
well-
to see this OSNAP line. Yeah, that's just what I said, like I can do the OSNAP line.
Yeah, I'm looking at it.
And it would be closer.
Subsurface TNS biases through the 1,000-meter range would be really good.
So the other part of it in terms of AMOC, you can have things coming through the Fairbank Channel. I don't know if that's contributing significantly here or convection in the Erminger Sea directly. So, I mean, models do all these different things that contribute to AMOC as you go further downstream.
And on that subject, there's the lab seat, which we haven't talked about, but the convection tends to be with that CR value as high as he has it, even though it's not as high as it was. The convection moves right across, right over to Greenland. You lower that coefficient in the Arctic, you can move that convection right across the lab sea to the other side. Okay, and because if you do that over the whole Arctic, you actually then increase the AMOC by a good 10% just by doing that one parameter change. But then that wouldn't make it symmetric with the south, and now you're really hand waving. But that's how sensitive things like, and that's part of the MOC too. That's how sensitive things are to this restratification. So it's not a tuning knob, it's a leading order thing that we have to understand and improve upon. Assuming there's room for improvement, Baylor.
That's what John Marshall said. It should be in the 90s. So we're just following up.
Yeah. It's exciting that that this process is a key piece to this everywhere.
You were gonna say something, I think. No? Okay.
Yeah. Yeah, sorry to show the overflow was kind of being cooked and just came in early this morning. But yeah, I don't understand either why, but I mean, I think we had a hint that the coordinate is influencing how much overflow and we should understand what's going on and how that affects AMOC.
So you mentioned the work in the CPT and the mesoscale. What's different, or are you using any backscatter in OM5 ¼ degree or any momentum closures besides Bioharmonics Mag?
Yes, ¼ degree this is most mature in our ESM 4.5, which we're trying to finalize now. Wenda Zhang has been working closely with John Dunn on putting in backscatter and trying out backscatter and GM, trying masking near the coast, a whole bunch of stuff.
So it's not finalized, it's still.
We have about 3 months. This is, as was noted here, these are changes that will contribute to that energetic intermediate water, low PV, and so the parameterizations are. We've been looking at exactly the same metrics with the same color scheme.
Oh, I got it from John Christen, so big thanks to him.
Oh, okay.
For the notebook.
Trying to do that, but yes, the intention is to try to use modest amounts of backscatter with GM.
Okay.
But it's not leafy, and so we haven't seen Tsuchiya jets, although maybe we'll go back and look.
Curious as to what it thinks.
So Bob, could I ask you a question from your talk?
Yeah.
One of the old biases we had, we never liked where the actual Gulf Stream went in the west. Is that solved and that's why it's not in any maps anymore? It seems nobody seems worried about it, or is it just?
So backscatter helps a lot. So this is Jenny Chang had a figure, and I kind of flashed it up.
Okay.
If you use backscatter, because I didn't dwell on it because I thought other people had kind of talked about backscatter enough. But backscatter, by kind of reinforcing some of the structures, helps with that. The challenge is that it tends to also give you a big wobble on the Blake Bahama Outer Ridge a little bit early. So you win further downstream, and so it's a little bit of a work in progress. And with any of these backscatter schemes, they are amplifying the eddies, they're amplifying mean structures.
Yes, they do.
And so figuring out how to say, okay, when do they not amplify mean structures? In particular for the Blake Bahama Outer Ridge, what we're looking at is if you are within a deformation radius or so of the coast, then you don't think the backscatter should be able to amplify in the same way because you're starting at topographic suppression. Instead of energizing eddies, you're going to be energizing topographic waves, but figuring out how to implement something that we're entirely happy with remains a bit elusive. But we do have one thing that fixes that problem. It doesn't help us so much in some other places, but it is a promising sign, and that's published. Chang et al. 2024, I think.
That's sure you think it's GRL, right?
Yeah.
On the mixed layer depth and convection, that's remembering from POP, it's very hard to actually change the biases. We kind of.
Well, in the Southern Ocean, there is no mixed layer. It's just a constant stratification down, and wherever you pick your criteria is where you hit. So
on that, we really like an energy-based criteria
Yes,
for
that's what I
figuring
guess
out how deeply you are homogenizing with a.
Yeah.
It removes all the old questions about, okay, do you use a temperature criteria? If you're in the Arctic, do you do something different? So we really like that much more robust energy-based criteria if we can persuade other people to look at it. It's available in MOM6 and easy enough to calculate in other cases.
It's the observations to compare it for comparison that we're lacking, that we made us step away from it for the, but I think we can do that for OMIP. We should just do it and produce those data sets. But it'll take a few years to sort that out.
But it, also, if you're working with Argo, it's much less sensitive to the question of when do you turn off Argo as you get close to the surface. Because it's integrated a little bit of stratification at the surface and it doesn't get in the way. And so
it makes a lot more sense, but we need the equivalent of the Boyer built carefully, thoughtfully by people who understand how the Argo do and don't work before we're ready to go.
You mentioned ocean heat content integrated online, and I know that with MOM 6 you could do diagnostics where it remaps, to Z or whatever you want, and it does that online.
Sure.
So it'll do the averaging just directly in Z.
Yeah.
Would that not be enough? That would be enough.
That's not.
Yeah.
That's definitely, and that was the goal, and we were talking with the NEMO folks as well, and so that's why we suggested hydrostatic pressure instead of Z, was because in Z star hydrostatic pressure is sort of at the ready in a way that it is not in the NEMO version of Z. And so we thought, and also we wanted to be closer to the observations, so be hydrostatic pressure, because we thought that would be more like the obs. And so putting all those pieces together, that was how we came up with the specification, but tried to make it light. And like I said, there's only 5 layers or so, because we don't want it to be a computational burden. We just want the ones that the observationalists produce these data sets for and get as close to them as we can.
but the observational, the levels are chosen to match the depth range of XBTs, the depth range
Exactly.
of Argo,
It's based on instruments. Yeah. It's a fundamental limitation of the data sets.
and those are ones where the reconstructions going back are actually robust, at least through 2005, and in some cases back further. So you actually have real observations.
Oh yeah, the upper 300, we go back to the 60s. I mean, it really actually works. Yeah. So it's worth doing it.
Really smart.
Yeah.
Related on the lab C, I think you have non-local effects of eddies coming across from Greenland and restratifying, and then I'm hearing about, and I think Bill was co-author on the paper on that. I'm hearing sensitivity of the location of convection to a length scale in the Bodmer parameterization. Is there any way those two aspects are related, or is that, excuse me?
Yeah, so Jonathan Lilly and I talked a lot about this. We're trying to make something that's more like a non-local version of the mixed layer parameterization or GM as well. It's kind of a tricky business. It's a little bit funny, but those eddies just really aren't they don't care about they care about the gradient where they're made and the gradient where they die, but not anything in between. And we don't have any parameterizations that do that in the horizontal.
Right.
Icebergs. Icebergs do that. Icebergs do that.
Well, the tidal ray mixing thing does that now too, right?
Yeah, but it doesn't track features. It's kind of an energy field.
Oh,
It's not phase. We don't preserve the phase, and we scatter into a spectrum. It looks an awful lot like a surface gravity wave field with all the same considerations and constraints.
It's not local though.
It's very non-local, but it doesn't track well-defined features like an eddy very well.
Right. Were you gonna say something, Frank?
Was everybody excited that we're moving into sort of stochastics now that we have backscatter in all the models? It's a new world. I mean, they're still deterministic as formulated, but we've opened the door to doing stochastic eddy parameterizations.
I don't understand what's the connection between backscatter and stochastic that you're referring. I don't get it.
Just that what the backscatter is doing wouldn't be that different if you use the stochastic stimulator instead of a negative viscosity. The negative viscosity keeps it deterministic in the formulation, but the target of what it's doing is kicking at it in a semi-random way. What's going on? It's stimulating eddies to grow even when they're not fully resolved. And you could have done the same thing with the stochastic formulation and gotten very similar. I mean, Ian showed us many years ago that you can probably do better with stochastics if you're willing to go there.
Right, yeah, that's sort of, I talked about that at Commodore in the low res model, but I just don't have time to work on it right now, so I'm picking it back up in the summer. But our current configuration actually has the stochastic correction to the equation of state that we developed with Alistair several years ago now. So that's actually turned on by default in our configuration.
Judith Berner has shown a pretty strong sensitivity at ENSO period or persistence to stochastics in the atmosphere. So I'm sort of excited to see how the backscatter in the ocean model might affect our ENSO persistence problem.
Yeah.
Did 127 didn't have the backscatter?
Yeah, we don't have any fully coupled with backscatter yet.
A long weekend, long end of the week here.
23 people online, Dan said.
Any questions online? Wendell.
So I have a question about your least plus E setup. So you said you initially wanted to just use the least viscosity, setting that CK to 0. But you ended up using 1, which is re-injecting a lot of energy. So did you compare that with a setup where CK is 0? So you just use the least viscosity without re-injecting energy?
Yeah, so that is actually the default now. So the whole purpose of this exercise was to use LiTI as a dissipation scheme, and then by mistake I turned on the backscatter and it got this whole new now avenue that we're following. But the default configuration uses LiTI without backscatter, and it improves. So the regular LiTI is too noisy. And Ian can talk more about it, what you did exactly.
Yeah, it's too noisy. The reason why we switched from the Leith backscatter or the Leith implementation that's in there to the LiTI without backscatter is because of the way that I define dx for an anisotropic grid is different. And it means that because the formula has like pi over dx to the whatever. And the way I defined it, I get a much bigger value of diffusivity in the equatorial band where we have refinement than the other version that's already in there. So if we only wanted to turn up viscosity in the equatorial band, which is what we wanted, I said, just switch it over and don't use backscatter. That's why we did it. And then he turned on the backscatter anyway, and it helped.
Just mention also, the emergence of these jets seems very sensitive.
Yeah.
Both the efficiency of the backscatter and the LiTI biharmonic coefficient. We drop down below 70, they disappear. If you go, higher than 85, those overturning cells on the equator get crazy strong.
Yeah, you get all kinds of crazy behavior above 85. The boundary currents in the equatorial region are all completely wrong, doing like what happens with the Gulf Stream. So it is pretty sensitive.
One of the ideas from the Commodore meeting that seemed to have a lot of cachet then was Julian Mack style filtering and then applying the parameterization on the filtered fields. I think it kind of entered into the conversation too late, perhaps, to be a good candidate for this round. But is that something that still has interest? Is anybody working on it? Is it something for CMIP 8 or 9?
Peter Korn has done a EDRIS TT-like proof that the ocean model equations, including GM and REDI, are only well posed if you filter first. They are not well posed with GM and REDI on the instantaneous fields. So there is good reason to do that, for sure.
I agree. I think there's good practical and theoretical reason to do it, but just I'm not aware that anybody has time to work on it right now in terms of implementation. As I unfortunately have to get back to campus for a meeting, which I'm already going to be late, but I will come back to the Southern Sun if you guys are heading there.
Thanks, Ian. All the day.
This stuff is ready to go. Southern Sun now?
Sure. There is talks going on in the other room if people have the energy. There's a Bad-Hunky's celebration.
Yeah.
But unless there's any other questions, I think we can
Yeah, that's great. Thank you, guys.